What happens when black holes collide? There's something profoundly eerie about the silence of space. It's a void so vast, so absolute, that even light, the fastest thing we know, can be swallowed by it. And deep within this void, hidden behind veils of warped space-time and gravitational terror, lie the most mysterious objects in the known universe, black holes. They are cosmic cannibals, silent destroyers, and keepers of secrets buried beneath their event horizons. But what happens when two of these dark titans collide? This isn't just the stuff of science fiction. Thanks to gravitational wave observatories like LIGO and Virgo, we now know that black hole collisions are real, spectacular events, so powerful they send ripples through space-time itself. But beyond what we can detect, there lies a realm of wild theories, speculative frontiers, and paradigm-challenging possibilities. What if these cosmic collisions do more than just shake the universe? What if they tear holes in it? In this journey, we'll explore the many incredible things that might occur when black holes collide. Some are grounded in established physics. Others push the boundaries of imagination. But each one offers a new lens on the mysteries of existence itself. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Let's begin with perhaps the most exotic and counterintuitive idea, the creation of a white hole. To understand the concept of a white hole, you must first understand its opposite, what we know as a black hole. A black hole is a region in space-time where gravity is so strong that nothing, not even light, can escape. It's a one-way trapdoor in the fabric of reality. Once something crosses the event horizon, it's gone. There's no turning back. But what if there was a reverse? A kind of mirror image in the laws of physics? This is where the theoretical idea of a white hole comes in. A white hole is like a black hole in reverse. Instead of sucking in matter and energy, it spews them out. Instead of being a point of no return, it's a point of no entry. In theory, a white hole is an area of space-time from which nothing can enter, only exit. Imagine an impossibly bright fountain erupting from nowhere, pushing matter into the universe without allowing anything to fall in. White holes aren't something we've observed, but mathematically, they are valid solutions to Einstein's field equations of general relativity. In fact, if you take the equations that describe a black hole and run them backward in time, you get a white hole. But why haven't we seen one? And more importantly, what could possibly create one? One idea proposes that a black hole collision, an unimaginably violent event, could provide the conditions for a white hole to form. When two black holes merge, the resulting energy, pressure, and space-time distortion may be so extreme that it momentarily destabilizes the very structure of the black hole itself. Instead of collapsing inward forever, the core might rebound, not unlike a cosmic ricochet. In this speculative scenario, the compression could reach a tipping point where quantum gravitational effects override classical ones. If this happens, the newly formed black hole might undergo a kind of quantum bounce, effectively reversing its gravitational signature. Instead of pulling in, it could start pushing out. That push, if sustained, would look a lot like what we describe as a white hole. This is not just idle fantasy. Some researchers working in loop quantum gravity, a candidate theory for unifying quantum mechanics and general relativity, suggests that black holes may not end in singularities at all. Instead, the collapse halts at a minimum size, then explodes outward in the form of a white hole. The idea is that space-time itself has a discrete structure at very small scales, like pixels in a digital image, and this structure resists infinite compression. When a black hole is pushed to the brink, this granular space-time may push back. In this framework, a white hole is not born immediately. It may take billions of years. But the birth could be accelerated if two black holes merge violently enough. The merger could act as a trigger, instantly transforming the new entity into a white hole or accelerating its timeline toward becoming one. Now, let's turn the lens outward. If a white hole did emerge from a black hole collision, what would we see? What signs would it leave in the universe? First, a white hole would be bright, perhaps blindingly so. It would radiate energy and matter in all directions, possibly explaining certain high-energy phenomena we don't yet fully understand, like gamma ray bursts or fast radio bursts. Some even speculate that these mysterious cosmic flashes could be linked to short-lived white holes bursting into existence. Second, a white hole might produce gravitational signatures very different from ordinary black holes. It would release gravitational waves during its formation, but with a frequency and pattern that doesn't quite match the standard ring-down phase of black hole mergers. Detecting such an anomaly could be the first indirect evidence of a white hole. There's also a speculative connection to the Big Bang itself. Some theorists have proposed that our universe may have originated from a white hole, a kind of cosmic rebound from a collapsing prior universe. This leads into the concept of cosmological white holes, where each white hole forms a new, separate universe on the other side. But that's a tangent we'll come back to later when we discuss baby universes. It's worth noting that most mainstream physicists are skeptical of white holes as real physical entities. The mathematics supports them, but without empirical evidence, they remain speculative at best. Moreover, they suffer from severe stability issues. Any infalling matter, even a single photon, would destroy a white hole or prevent its formation according to classical theory. This raises a paradox. How can a white hole exist in a universe filled with background radiation and particles? This is why the idea that black hole collisions might create white holes is so intriguing. It offers a rare exception. In a collision, the conditions are not ordinary. For a brief instant, the universe might allow the impossible. A region of space-time so chaotic, so warped, that it bypasses the usual rules. If a white hole could ever form, this might be how. And if white holes can form, suddenly, explosively, then they could be one of the strangest fireworks in the cosmos. Not just violent ends, but impossible beginnings. Not just death, but rebirth. Multiverse tunneling. What if when black holes collide, they don't just disrupt the fabric of our universe, they punch through it entirely? In the vast arena of theoretical physics, few ideas are as mind-expanding as the multiverse. The notion that our universe is but one bubble in a vast cosmic foam of many others, a multiverse, has captured the imagination of scientists and storytellers alike. But while the multiverse is a compelling concept, it comes with a major caveat. Even if other universes exist, how would we ever reach or detect them? One radical idea suggests that the answer might lie in the cataclysmic union of two black holes. When black holes collide, they don't just merge, they detonate the structure of spacetime. The gravitational forces at play during a merger are so powerful that they can tear through the continuum of space and time like a razor through silk. This tearing, some theorists propose, might not just distort our universe. It could open a tunnel to another one entirely. The idea is grounded in a blend of quantum gravity, string theory, and brane cosmology. In some models of string theory, our universe is a three-dimensional brane, short for membrane, floating in a higher dimensional space known as the bulk. Other branes, other universes, could be hovering parallel to ours, just out of reach. Normally, we're isolated from them by the separation in higher dimensional space. But what if something could breach that gap? Enter the black hole collision. The immense energy released when two black holes collide could be enough to deform our brane to the point where it momentarily intersects with another brane. That intersection could be a tunnel, a fleeting bridge between universes. This wouldn't be a simple portal like in science fiction. It would be a rupture in the higher dimensional fabric of reality itself. The merging black holes might act as a transdimensional scalpel, slicing through the bulk and creating a one-time passage. This concept is sometimes referred to as quantum tunneling between universes, drawing a metaphor from the quantum phenomenon where particles pass through barriers they seemingly shouldn't be able to cross. At the quantum level, what seems impossible isn't just possible, it's common. Particles routinely pop in and out of existence, or appear on the other side of barriers they lack the energy to overcome. Could the same principles apply at the macro scale of cosmic events? Some versions of this theory suggest that information, matter, energy, or even consciousness, could be transferred from our universe to another during such a collision. That transfer might be minuscule or massive, depending on the nature of the breach. Others hypothesize that the black hole merger doesn't just connect two universes, it births a new one, a point we'll explore more deeply when we discuss baby universe creation. Let's imagine what this would look like. From our perspective, we might not see the tunnel form at all. Instead, we might observe a merger that ends with an unexpected silence. Instead of the expected ring-down phase, where the new black hole vibrates and emits a predictable signature of gravitational waves, we might detect an abrupt cutoff, or a strange anomaly in the waveform. That could be evidence that some portion of the system didn't remain in our universe. Alternatively, we might detect gravitational wave echoes or fluctuations that hint at exotic interference, something pulling or pushing against our side of the merger from the outside. These echoes could be residual vibrations from the other side of the breach, a neighboring universe reacting to the collision on ours. There's also the tantalizing idea that runaway pulsars, high-speed neutron stars ejected from supernovae, could be connected to failed or partial tunneling events. Perhaps they're not just kicked away by black holes or gravitational dynamics. Perhaps they've brushed up against a dimensional tear and been slingshot by physics we don't yet understand. Now, let's be clear, multiverse tunneling is, for now, pure speculation. There is no empirical evidence of such bridges, nor a concrete model in standard physics that predicts them. But some corners of theoretical physics leave room for their possibility, especially those that unify gravity with quantum mechanics. In particular, string theory and M-theory deal with higher dimensional spaces where such events, while incredibly rare, are not outright impossible. Interestingly, this idea is also related to black hole entropy and information paradoxes. If black holes can serve as gateways to other universes, it might offer a solution to where the information goes when a black hole evaporates. Instead of being destroyed, the information could be transferred to another realm entirely, sidestepping the paradox altogether. Could this be a way for the universe to recycle itself? To bleed entropy into fresh cosmic landscapes? Perhaps every black hole merger is a branching point in a cosmic decision tree, carving tunnels to places forever beyond our observational reach. Or perhaps not. Maybe these collisions shake the very walls of the cosmic prison we inhabit, and every now and then, a small crack forms in the cell. A crack not wide enough to escape through, but wide enough to glimpse the infinity beyond. Until we understand more about quantum gravity, space-time geometry, and the structure of the multiverse, if it exists, multiverse tunneling remains a brilliant, breathtaking possibility that sits on the very edge of science. But if it ever does happen, if we ever observe an anomaly so wild, so unexplainable, that it demands a multiversal explanation, then we'll know. We'll know that when black holes collide, they don't just reshape the universe, they may connect it to others. Wormhole formation. It's a concept that defies our ordinary perception of reality, a shortcut through spacetime, a cosmic tunnel that connects distant regions of the universe, or perhaps even different universes altogether. Known as wormholes, these fantastical structures are the staple of science fiction, yet they originate from real equations in Einstein's theory of general relativity. And one of the most provocative ideas in modern astrophysics is that when black holes collide, they might not simply merge, they might tear open spacetime itself and form a wormhole. Let's start with what a wormhole actually is. The formal name for a wormhole is an Einstein-Rosen bridge, a hypothetical tunnel with two ends, each in separate points in spacetime. Picture spacetime as a 2D sheet. A wormhole folds that sheet and punches a tunnel through the fold. If you could enter one end of a wormhole, you could exit from the other end, potentially billions of light years away, or even in another time. These ideas aren't just artistic, they're solutions to Einstein's equations. But there's a catch: wormholes are inherently unstable. Under most models, they collapse too quickly for anything to travel through them. To keep them open, you need something exotic, negative energy, or exotic matter, a substance with properties not found in any known material. But here's where black hole collisions come in. When two black holes spiral into one another, they produce a region of extreme curvature in spacetime. It's not just bent, it's torn, twisted, and flung around with unimaginable force. The gravitational fields involved in the merger are so extreme that, for a brief moment, the structure of spacetime may become malleable. It's in these fleeting instants that some theorists believe a wormhole might spontaneously form, or that a pre-existing microscopic wormhole could become activated or enlarged. How would this happen? In some versions of quantum gravity or higher dimensional models, spacetime isn't smooth but foamy at the smallest scales, the so-called spacetime foam. Imagine countless tiny wormholes popping in and out of existence at the Planck scale, the smallest scale in physics. Under normal circumstances, they're insignificant. But the sheer energy and curvature generated during a black hole collision might cause one of these microscopic wormholes to inflate, stretching it into a macroscopic tunnel that briefly becomes traversable. This wormhole wouldn't last long, it might snap shut almost immediately, but during its brief existence, it could offer a real, physical pathway between widely separated points in spacetime. If the ends of the wormhole stabilized or anchored themselves to mass in different parts of the universe, the wormhole could even persist, though this would likely require unknown physics or exotic matter to hold it open. Another possibility is that the black hole merger doesn't create a wormhole between two distant locations in our universe, but instead between our universe and another one. This would make the wormhole interuniversal, forming a tunnel through the higher dimensional bulk, in line with certain brain-world theories from string theory. Now let's explore what we might detect if this were the case. Suppose a wormhole formed momentarily during a black hole merger. What could we observe? First, there might be anomalies in gravitational wave signals. Wormhole formation could leave behind signatures unlike those from ordinary mergers, perhaps strange echoes, or missing energy that appears to vanish into the wormhole. If something escaped through the tunnel, the resulting black hole would be lighter than expected, violating the usual rules of mass energy conservation in our visible universe. There could also be electromagnetic effects. The sudden formation or collapse of a wormhole could unleash energy bursts, similar to short gamma-ray bursts or high-energy neutrino events. These events might be mistaken for more common astrophysical phenomena unless they occur in direct synchronization with a black hole merger detected via gravitational waves. The wildest speculation of all is that something could come through the wormhole. Maybe information, maybe particles, maybe entire systems. Some speculative models even suggest that civilizations, if advanced enough, could have seeded or stabilized wormholes across the cosmos for interstellar travel. If black hole collisions spontaneously produce these cosmic tunnels, they might be a natural phenomenon that intelligent life could one day harness. There's also a curious connection to entanglement and quantum mechanics. In 2013, a surprising conjecture known as ER=EPR was proposed by Leonard Susskind and Juan Meldacena. It suggests that wormholes, Einstein-Rosen bridges, and quantum entanglement, Einstein-Podolsky-Rosen pairs, might actually be two sides of the same coin. If this is true, then the formation of a wormhole during a merger could be intimately tied to the deep quantum structure of reality, possibly revealing how space itself is stitched together by entanglement. Of course, there are problems. Wormhole formation remains highly speculative, and some physicists argue that any wormhole formed during a black hole merger would be hidden behind the event horizon, forever out of reach. Others argue that the intense tidal forces during the merger would immediately collapse any wormhole structure. There's also the lack of empirical evidence. We've yet to observe anything that conclusively points to wormholes, despite decades of looking. Still, the possibility lingers. It lingers because we don't yet understand the true nature of black holes, nor the quantum fabric of spacetime. And every black hole merger offers us a laboratory, one we can't visit, but can listen to through gravitational waves. So when two black holes collide, they may do more than just merge. They may, for a breathless instant, twist the universe into a new shape. And in that shape, a tunnel may open, a tunnel to elsewhere. To elsewhen. To the ultimate cosmic shortcut. Dimensional leakage. Imagine watching two black holes collide, a titanic release of gravitational energy, shaking the very fabric of spacetime. But what if we're not seeing the whole picture? What if some of that energy doesn't stay in our universe at all, but leaks out, slipping silently into unseen dimensions beyond our perception? This is the core of the dimensional leakage hypothesis, an idea born from attempts to unify gravity with the quantum world, and one that might just be testable through black hole collisions. Let's begin with the premise. We live in what appears to be a three-dimensional world, left/right, up/down, forward/backward, plus the dimension of time. But many advanced theories in physics, particularly string theory and its relatives, suggest that there are more dimensions than we can observe. Some models posit 10, 11, or even more dimensions of space, most of them compactified, curled up at scales too small for us to see. So if extra dimensions exist, why haven't we detected them? One answer is that the forces of nature are confined differently. The electromagnetic, strong, and weak nuclear forces appear to be restricted to our familiar three-dimensional brain. But gravity, the weakest and most mysterious of the fundamental forces, might be able to extend into the bulk, the higher dimensional space that contains our brain. This idea is central to brain world models, like those proposed in the Randall-Sundrum theories. Now, picture what happens when two black holes spiral into one another. The gravitational wave energy emitted during this collision is immense, far more powerful than anything else we can observe. If any process could probe or interact with extra dimensions, this would be it. According to some models, during such a high-energy, high-curvature event, the gravitational fields may become so extreme that a portion of the energy, perhaps even entire ripples of space-time, can escape into the extra dimensions. This is dimensional leakage. From our point of view in the 3D brain, it would appear as if energy has mysteriously vanished. We would observe a discrepancy in the energy balance of the merger. The gravitational waves we detect would be slightly weaker than predicted, or oddly distorted. The final black hole might end up with less mass than expected, and there might be no trace of where the missing energy went, because it left our universe. But how could we ever test this? Gravitational wave detectors like LIGO, Virgo, and CAGRA already observe the subtle ripples from black hole mergers. By comparing the observed waveforms with theoretical models, scientists look for anomalies, departures from the standard templates. If, for example, the merger emitted only 90% of the energy we expect, and no matter or light explains the missing 10%, it could suggest that the remainder leaked into extra-dimensional space. Some experimental physicists have proposed using next-generation gravitational wave detectors, like LISA, Laser Interferometer Space Antenna, to explore this possibility more directly. These instruments would be more sensitive to low-frequency gravitational waves, such as those produced by supermassive black hole mergers, prime candidates for dimensional leakage. Now let's delve into the theoretical mechanics of how this leakage might happen. In certain string theory-inspired models, gravity is fundamentally a higher dimensional interaction, and what we feel as gravitational force is merely the residue of this interaction projected onto our brain. So during a black hole collision, some of the curvature energy, especially if it's tightly concentrated, might momentarily interact with the bulk. This could allow gravitons, hypothetical particles that mediate gravity, to radiate into the extra dimensions, removing energy from our universe. It might also occur via the activation of Kaluza-Klein modes. These are higher dimensional versions of particles that only emerge when extra dimensions are involved. In theory, the black hole collision could excite these modes, effectively spending energy to create vibrations in dimensions we can't access. More radically, some theorists suggest that black hole mergers could cause tears or punctures in the brain, temporary rips that allow bulk space to flood in, or for our space to vent energy outward. These rips would be tiny, short-lived, and would likely heal rapidly, but they could allow measurable losses during the event. And here's where it gets truly bizarre. What if these leaks don't just release energy, but allow entities or particles from the bulk to enter our universe? There are speculative hypotheses that suggest bulk space might contain exotic forms of matter, or that certain dark matter candidates, like axions or sterile neutrinos, might originate from higher dimensions. A black hole collision might offer a one-way gateway through which such particles could enter our universe, appearing suddenly and without an identifiable source. This brings us to one of the strangest possibilities: dimensional memory. What if, even after the energy leakage event, the final black hole retains memory of the interaction with extra dimensions? Its spin, charge, or ring-down vibrations might carry hidden signatures, subtle deviations that hint at interactions beyond our space. These signatures could be the key to understanding not only extra dimensions but the quantum structure of spacetime itself. However, all of this remains highly theoretical. No current black hole merger has shown direct evidence of dimensional leakage. The gravitational waves observed so far match Einstein's predictions with high precision. But that doesn't rule it out. It just means that if leakage happens, it's either very subtle or occurs only under specific, rare conditions. Perhaps we simply haven't yet seen a collision big enough, or a merger violent enough to tear through the boundaries of our dimensional prison. If one day we do observe a black hole collision that refuses to obey the rules, if we hear a gravitational whisper, where there should have been a shout, or find mass mysteriously missing from the aftermath, then we may have our first clue. A clue that our universe is not the whole of reality. That just beyond the veil of perception, a wider world exists. A multidimensional realm, stitched together with gravity and energy, waiting for the next black hole to open the door. Time reversal zones. Time, the great river we all drift along, seemingly forward without pause or possibility of return. But what if, in the most extreme corners of the cosmos, that river doesn't just flow, it loops, reverses, and folds in on itself? What if time, during the violent merger of black holes, doesn't just slow down or dilate, but runs backward? Welcome to the theory of time reversal zones, a frontier of physics where direction, causality, and the very notion of before and after collapse under the gravitational pressure of colliding singularities. To explore this theory, we must first appreciate a fundamental truth of modern physics. The laws of nature are, mostly, time-symmetric. That means the equations that describe electromagnetism, gravity, and even quantum mechanics remain valid whether time moves forward or backward. If you recorded a planet orbiting a star and played it in reverse, the math still checks out. This symmetry is so deeply embedded in our physics that its violation, as in weak nuclear decay, is extremely rare and very specific. But in our everyday experience, time has a direction, the so-called arrow of time, which always points from past to future. This direction arises not from fundamental physics, but from entropy. The second law of thermodynamics says that systems tend to evolve toward disorder. A glass breaks but does not unbreak. Smoke rises and dissipates but doesn't gather itself again. This is the entropic arrow of time. Now consider a black hole, a place where time itself is distorted. Near the event horizon, gravitational time dilation becomes so intense that, from the perspective of an outside observer, time appears to freeze at the edge. For the object falling in, time continues normally, but for distant viewers, the fall stretches toward infinity. Now push this further. Imagine two black holes merging, each with their own warped space-time geometries, each distorting time in extreme and nonlinear ways. As they spiral toward collision, their event horizons stretch and twist spacetime like wet cloth in a whirlpool. At the moment of merger, where densities and curvatures approach infinity, the structure of spacetime may no longer preserve the forward flow of time in every region. Instead, closed time-like curves, CTCs, may form, or more radically, time-reversed zones might emerge. But what are these zones? In simple terms, a time-reversed zone is a region where the thermodynamic arrow of time runs backward. That means, inside this region, cause and effect could flip. Effects might precede their causes. Signals sent into the zone could return before they were emitted. If matter or information exists inside, it might appear to unevolve, becoming more ordered, more structured, defying the second law, at least locally and temporarily. These time reversal zones could be bounded, hidden within the warped geometry of the merged black hole, or they might flare outward during the collision, momentarily touching the outside universe. The idea isn't entirely speculative. In certain solutions to Einstein's field equations, such as the Gödel metric or Tipler's rotating cylinder, closed time-like curves naturally arise. These solutions are mathematically valid, though physically controversial. During a black hole merger, the extreme angular momentum and frame dragging might temporarily generate regions where time loops or reverses. The collision could also recreate initial conditions so precisely in a localized region that entropy momentarily drops, creating a bubble where time seems to run backward relative to the rest of the universe. This could occur through ultrasymmetric energy configurations or perfect cancellation of gravitational radiation in specific directions. But let's push this further into speculative territory. If time-reverse zones truly exist, what happens to information within them? One possibility is that information bounces back, returning from the future into the past. This might help solve the black hole information paradox, in which quantum information seems to be lost behind event horizons. Perhaps time-reverse regions serve as reflectors, bouncing quantum data back into the universe, preserving unitarity, the principle that information must not be destroyed. Another radical idea: these zones could be gateways to retrocausal phenomena. Imagine detecting a burst of gravitational waves that precede a black hole merger, echoes from the future. Or worse, imagine that certain cosmic phenomena we observe are the results of future black hole collisions that have already reached back in time. There are some hints, however faint, that we might someday be able to test these ideas. Gravitational wave signals from black hole mergers are precise, and they decay in a very specific pattern called the ring-down. If anomalies appear, if we detect pre-merger echoes, non-local delays, or strange symmetries in the waveform, it could suggest the presence of time-reverse structures. Moreover, researchers have proposed looking for negative entropy flows in gravitational wave data. If any region in the event shows decreasing entropy, it might indicate a localized reversal in thermodynamic time. This is still an idea in its infancy, but one that quantum gravity theorists are paying attention to. Now, let's ask the forbidden question: what would happen if you entered a time reversal zone? Assuming you could survive the tidal forces, a very big assumption, your subjective experience might be completely normal. You'd still feel time moving forward. But to the outside universe, your actions would appear reversed. Your words, your heartbeat, your motion, they'd unfold backward. You might unage, returning to a prior state before disappearing into the event horizon again. From our perspective, you'd be a traveler not through space, but through reverse causality. In extreme cases, if these zones are large enough or stable enough, they could function as time machines, allowing information or even particles to travel backward in time relative to the external universe. This would raise deep paradoxes, grandfather paradoxes, bootstrap loops, and potential violations of causality that challenge the very foundation of logic and physics. Yet, there's a safety mechanism built into the universe, perhaps. It's called the chronology protection conjecture, proposed by Stephen Hawking. It suggests that nature conspires to prevent time travel by destroying or destabilizing any configuration that permits causality violation. If time-reverse zones emerge during a black hole merger, they may be violently unstable, collapsing instantly under quantum fluctuations before they can allow paradoxes. And yet, what if just for a fraction of a second time bends? What if the aftermath of a black hole collision isn't just a larger black hole, but an event with no fixed sequence, where future and past intertwine, and cause and effect become whispers rather than commands? We may never know. Or perhaps we already do, and just haven't realized it yet. Because somewhere in the gravitational echoes of a far-off black hole collision, time may already be running in reverse. Dark matter particle emission. In the vast cosmic theater, dark matter is the invisible performer shaping galaxies, bending light, and governing the structure of the universe, yet it neither shines nor absorbs. It is utterly dark. Despite decades of study, we still don't know what it is. But some theories suggest we might catch a glimpse, not through light, but through the ripples in spacetime itself. When two black holes collide, their merger unleashes incomprehensible energy. Vast amounts of mass, sometimes multiple solar masses, are converted directly into gravitational waves in mere seconds. The conditions are so extreme that the very fabric of the universe becomes molten, warped, and fluid. It is within this crucible that dark matter particle emission may occur. Let's start with the basic idea. Most known dark matter candidates, such as WIMPs, weakly interacting massive particles, axions, or sterile neutrinos, are hypothesized to interact extremely weakly with normal matter and light. This is why dark matter passes through stars, planets, and even you, without leaving a trace. But under the most intense gravitational or quantum conditions, these particles might be produced, altered, or even released from hidden realms. Enter the black hole merger. During the final instance of a collision, the extreme compression of spacetime could act as a quantum furnace, briefly replicating energy densities similar to those in the early universe, just moments after the Big Bang. According to particle physics, such conditions are perfect for phase transitions, particle creation, and symmetry breaking, events that could generate dark matter particles en masse. One hypothesis is that virtual particles trapped near the event horizons could be forced into real existence during the violent merger. This is somewhat analogous to Hawking radiation, but on a more energetic, violent scale. If dark matter particles exist in the vacuum, appearing and disappearing constantly as quantum fluctuations, then the merger could provide enough energy to pull them out permanently, liberating them into the cosmos. But there's another angle. What if dark matter is already there? Some scientists propose that primordial black holes formed not from collapsing stars, but directly from quantum fluctuations in the early universe, might themselves be a component of dark matter. If such primordial black holes are merging, the collision might not just emit gravitational waves, but also trigger particle emission events specific to their internal exotic structure. Additionally, dark matter might accumulate near black holes, trapped in the gravitational well. These dark halos would be invisible but could be disturbed or ejected during a merger. When two black holes collide, any bound dark matter could be squeezed out, forming jets of exotic particles that stream away at relativistic speeds. These particles wouldn't be visible, but they might leave indirect effects, such as recoils, missing energy, or non-standard waveforms in the gravitational radiation. Now let's explore a more speculative but fascinating idea: new particle production through symmetry breaking. During black hole collisions, spacetime curvature can become so intense that it causes temporary violations of standard symmetries, like charge conjugation, parity, or even lepton and baryon number. In such a situation, new physics could emerge, allowing non-SM, standard model, particles to form. These might include stable, massive particles that don't interact electromagnetically, in other words, perfect dark matter candidates. Some proposals also link dark matter to supersymmetry, SUSY, a theoretical extension of the standard model that predicts every known particle has a superpartner. While supersymmetry remains unproven, if real, then the energies produced in black hole mergers might be sufficient to briefly excite or reveal these superpartners. The lightest of them, such as the neutralino, could be stable and weakly interacting, again, matching dark matter's profile. Now, let's look at how we might detect this. Gravitational wave observatories like LIGO and Virgo are incredibly sensitive to disturbances in spacetime. If dark matter particle emission subtly alters the waveform of the black hole merger, say, by creating asymmetries, or by carrying away energy in non-radiative forms, then these deviations could be detected as anomalous gravitational signatures. For example, abrupt damping of the ring-down signal might suggest unseen energy escaping. Non-Gaussian noise components could hint at interactions with exotic fields. Irregular recoil velocities of the final black hole might suggest momentum transferred to escaping particles. Another possible detection method involves multi-messenger astronomy. While black holes themselves emit no light, if dark matter particles interact very weakly with normal matter, some of them might produce faint gamma rays, neutrino bursts, or radio anomalies upon scattering with interstellar material post-merger. Coordinated observations across the electromagnetic spectrum might reveal these elusive signatures. And here's a chilling thought: what if a fraction of the missing mass in black hole mergers isn't going into gravitational waves at all, but into a dark particle outflow that we simply can't see, particles that float silently through the cosmos, adding to the invisible scaffolding that holds galaxies together? This raises another question: could black hole collisions be factories of dark matter? Perhaps some fraction of the total dark matter in the universe didn't form in the Big Bang but was created later, through the continual merging of black holes over cosmic time. This would provide a new timeline for dark matter production and could help explain its distribution in halos around galaxies, especially if black hole collisions tend to occur more frequently in galactic centers. Yet another theoretical layer involves dark sectors, entire hidden universes of particles that interact with each other but not with us, except through gravity. Black hole mergers might disturb the barrier between our sector and the dark sector, causing cross-sector transitions where energy or particles pass from one realm into another. This could account for unexplained mass loss and might suggest that our visible universe is just one piece of a larger, more complex puzzle. In some speculative models, dark photons, hidden scalars, or Z-bosons, hypothetical dark force carriers, could be emitted during mergers, providing a completely new portal into unseen physics. These particles wouldn't show up in any telescope but might subtly change the way the gravitational wave behaves, an invisible whisper riding on the loud roar of colliding black holes. Of course, all of this is still theoretical. We haven't yet detected direct evidence of dark matter particle emission from black hole mergers. But with more advanced detectors, such as Einstein Telescope, LISA, and Cosmic Explorer, on the horizon, the sensitivity of gravitational wave astronomy is about to increase dramatically. When that happens, we might find anomalies. Mass that goes missing. Energy that can't be accounted for. Bursts of motion that suggest an unseen hand. And in those echoes, we might hear the silent song of dark matter being born. Perhaps, at the heart of darkness, when two black holes merge, the universe writes another line in the great story of the unseen. And for the first time, we might be able to read it. Vacuum instability trigger. At the frontiers of theoretical physics lies a terrifying question: what if the vacuum of space is not truly stable? What if everything we know, particles, forces, atoms, even the laws of physics, rests on a fragile foundation, one that could collapse at any moment under the right conditions? This concept is called vacuum metastability, and it revolves around the idea that our universe might not occupy the lowest possible energy state, but instead exist in a false vacuum, a temporary plateau of stability. It's a bit like a ball resting in a shallow dip on a hill rather than at the true bottom of the valley. The ball may seem still, but if it's nudged hard enough, it could fall, and once it starts rolling, there's no stopping it. That nudge could come from the collision of two black holes. Let's unpack this. In quantum field theory, the Higgs field permeates all of space, and the mass of the Higgs boson, discovered in 2012 at CERN, tells us something profound about the shape of the vacuum potential. Based on the current mass measurements of the Higgs, 125 GeV, and the top quark, 173 GeV, theoretical models suggest that the vacuum may not be entirely stable. Instead, it's metastable, stable for now, but with the potential to decay. Now imagine a black hole merger, two unimaginably dense singularities spiraling into each other, tearing space-time, heating it to billions of degrees, and concentrating more energy than a million supernovae in a fraction of a second. The environment during such a merger could, in principle, reach Planck-scale energies, energies where the smooth geometry of space-time breaks down and quantum gravity takes over. If our vacuum is metastable, then the conditions during a black hole collision might push a tiny region of space over the energy barrier separating the false vacuum from the true vacuum. And what happens if that barrier is crossed? A bubble of true vacuum could form, an expanding sphere where the laws of physics are radically different. This bubble would grow at nearly the speed of light, consuming the false vacuum as it spreads. Particles would cease to exist. Forces might be altered or erased. The very fabric of reality would be rewritten in its path. No warning. No escape. No defense. This event is known as vacuum decay, and once triggered, it's unstoppable. The entire observable universe could vanish in a blink, not through explosion, but through transformation. It wouldn't be the end of the universe. It would be the rewriting of its operating system. Now, before we spiral into existential dread, it's important to emphasize, this scenario is ultra-hypothetical. There's no evidence that such an event has ever occurred, or that black hole collisions have ever triggered vacuum decay. In fact, nature seems to prevent such catastrophic instabilities. The universe has seen countless high-energy events, quasars, supernovae, gamma-ray bursts, and yes, black hole mergers, yet reality remains uncracked. One reason might be that quantum tunneling into a lower vacuum state is probabilistic and extraordinarily rare, so rare that even the most violent event we can imagine can't force it. Another possibility is that quantum gravity, the yet-to-be unified theory combining general relativity with quantum mechanics, might protect against such instabilities. Some theorists also suggest that black hole event horizons themselves may shield the surrounding vacuum, acting as a sort of firewall that contains or absorbs high-energy fluctuations before they can escape and seed a vacuum decay. Others point out that if vacuum decay were triggered inside the event horizon of a black hole, it would remain hidden, doomed to collapse into the singularity without affecting the outside universe. But that's only comforting if you believe the trigger can't occur outside the horizon, say, in the surrounding space-time deformed during the merger. Still more speculative is the idea that vacuum decay has happened in other parts of the universe, but we simply haven't been reached by those expanding bubbles yet. In that case, we wouldn't know. We can't know. The moment one reached us, we'd be annihilated faster than the brain could process the event. But let's turn back to the black hole mergers. Could these cataclysmic collisions genuinely be vacuum triggers? Could two black holes, as they merge into a larger one, create a region where spacetime is so curved and energy is so focused that the false vacuum pops into the true vacuum? Some physicists argue that the answer is no. Even the energy of colliding black holes may not be sufficient to create the specific field conditions needed to breach the vacuum barrier. After all, cosmic rays bombard Earth with energies exceeding those produced in human-made accelerators, and yet no vacuum bubbles have formed. Nature, it seems, may be more stable than our worst fears. However, others aren't so sure. Some fringe theories suggest that under specific quantum conditions, especially involving non-minimally coupled fields, Planck-scale particles, or hidden scalar fields, black hole collisions might serve as the perfect triggering event. If that's true, then each merger might carry a minuscule but non-zero probability of initiating vacuum decay. In this context, black hole collisions become not just a cosmic spectacle, but an existential roll of the dice. The risk may be infinitesimally small, but with enough time, and enough mergers, the odds start to add up. If such a decay ever happens somewhere in the cosmos, we will not see it coming. It will arrive like a silent wave, washing away the universe we thought we knew. This theory is controversial. It's frightening. It feels like a cosmic horror story written by quantum field theory. But it's also a reminder of how little we truly know about the deep structure of the vacuum, and how much remains hidden behind the veil of equations and probabilities. The vacuum seems empty, but it is not. It is a simmering sea of quantum fields, constantly in flux, restless and seething beneath its still surface. And when two black holes collide, they might disturb that sea just enough to reveal what lies beneath. We continue to study these collisions not only to understand black holes but to test the very stability of reality. Until we know more, each detection of gravitational waves from a black hole merger is not just a celebration of astrophysical discovery, it's also a quiet sigh of relief. The vacuum held. Again. Creation of a baby universe. Black holes have long been considered cosmic mysteries, objects so dense and gravitationally intense that not even light can escape their grasp. Yet what happens inside them is still largely unknown. The event horizon, the point of no return, shields us from direct observation, and the singularity, where classical physics breaks down, remains a profound enigma. The notion that a black hole might birth a baby universe arises from the interplay of general relativity, quantum mechanics, and cosmology. It's a theory that challenges our understanding of space, time, and even the concept of universe itself. Here's the basic idea. When two black holes collide and merge, their combined mass and energy concentrate into an incredibly dense core. The intense gravitational field warps spacetime in extreme ways. According to some cosmological models, this extreme environment could pinch off a portion of spacetime from our own universe, creating a bubble or pocket universe that inflates and evolves independently inside the black hole's interior. This baby universe would be causally disconnected from our own, meaning no information or matter could travel back to our universe from inside it. To an outside observer, it would simply look like one larger black hole. But inside, a new cosmos with its own laws, particles, dimensions, and even possibly different physical constants could be growing. This concept draws inspiration from the idea of cosmic inflation, the rapid expansion of the early universe shortly after the Big Bang. Inflationary theory suggests that the universe started as a tiny quantum fluctuation and expanded exponentially, smoothing out irregularities and setting the stage for the cosmos we observe today. In a similar way, the core of a black hole merger might act as a seed for a new inflationary phase, a tiny universe budding off like a cosmic offspring. Some key ideas supporting baby universe creation in black hole mergers include 1. Space-time wormhole connections. Certain solutions to Einstein's equations, especially those involving wormholes, hint at the possibility of bridges or tunnels to other regions of spacetime, some of which could be new universes. 2. Quantum gravity and singularity resolution. While classical general relativity predicts the singularity, a point of infinite density and zero volume, many quantum gravity theories propose that singularities are replaced by non-singular, finite structures. These could serve as the seed, or nucleus, of a baby universe. 3. Theoretical models of universe creation. Physicists like Lee Smolin have proposed cosmological natural selection, where black holes give birth to new universes with slightly different physical parameters. Universes with more black holes produce more baby universes, leading to a form of cosmic evolution. 4. Energy and information flow. The mass and energy of the parent universe collapse into the black hole, but within the baby universe, these quantities could remanifest as the energy driving inflation, matter formation, and cosmic evolution. 5. Causal disconnect. From our vantage point, the baby universe is hidden behind the black hole's event horizon, inaccessible and isolated. This means the baby universe can evolve independently without violating causality or observable physics. This idea has profound implications. It suggests that black holes are not just destructive cosmic endpoints but may be cosmic wombs, giving birth to new realms of existence. Furthermore, if baby universes do form inside black holes, the collision and merger of black holes might be the most prolific mode of universe creation in the multiverse. Each merger would represent a cosmic birth event, continually seeding new realities. Critics caution that this remains speculative. The physics inside black holes is still a theoretical frontier, and no direct evidence exists for baby universes. Yet, this hypothesis ties together several unsolved problems: black hole information paradox, quantum gravity, and cosmic origin questions, into a unified framework. If true, the collision of black holes would be both an end and a beginning. Two massive bodies collide and vanish into one, but hidden within their union, a new universe begins to unfold, growing quietly in the shadowed depths beyond our reach. Imagine the poetic grandeur of that, a cosmic phoenix, rising from the ashes of colliding black holes, birthing a new universe in every violent merger. Gravitational wave emission. When two black holes spiral toward each other and merge, they do more than simply combine their mass and energy. They create one of the most powerful disturbances in the fabric of the cosmos itself. These disturbances are called gravitational waves, ripples in spacetime that travel outward at the speed of light, carrying energy and information about their cataclysmic origins. The idea of gravitational waves originates in Albert Einstein's theory of general relativity, published in 1915. Einstein predicted that massive accelerating bodies would produce ripples in spacetime, much like a stone dropped into a pond creates waves on the water's surface. For decades, gravitational waves remained a theoretical prediction, as their incredibly weak effects were beyond the reach of observational technology. That changed dramatically on September 14, 2015, when the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration made the first direct detection of gravitational waves. The waves they observed originated from a merger of two black holes about 1.3 billion light-years away. This discovery opened a new window on the universe, Gravitational wave astronomy. Black hole collisions produce gravitational waves in three main phases. 1. In spiral. The two black holes orbit closer and closer together, losing energy by radiating gravitational waves. As they approach, their orbits accelerate, and the frequency and amplitude of emitted waves increase, a chirp signal. 2. Merger. The black holes collide and combine, producing a sharp peak in gravitational wave emission. This phase lasts just milliseconds but releases tremendous power, more energy than all the stars in the observable universe combined during that instant. 3. Ring down. The newly formed black hole vibrates and settles into a stable state, emitting gravitational waves as it rings, like a struck bell until the distortions fade. The amplitude of these waves is extraordinarily small by the time they reach Earth, on the order of a fraction of a proton's diameter over kilometers of detector length. Yet with exquisitely sensitive laser interferometers, scientists can measure these minuscule space-time distortions. Why are gravitational waves from black hole mergers so important? Probing extreme gravity. They provide direct information about the behavior of space-time under conditions of immense curvature and energy density, testing general relativity in regimes previously inaccessible. Understanding black hole properties. From the waveforms, scientists extract the masses, spins, and orientations of the merging black holes, revealing details about their origins and evolution. Cosmology and astrophysics. Gravitational wave detections allow measurement of cosmic distances and expansion rates, shedding light on the large-scale structure of the universe. Discovery of exotic phenomena. Wave signatures may reveal unexpected physics, such as deviations from classical black hole predictions, existence of primordial black holes, or hints of extra dimensions. Importantly, gravitational waves carry energy away from the system, causing the black holes to lose orbital energy and spiral inward faster until they finally merge. This energy loss can amount to about 5% of the combined mass energy of the system, a staggering release in pure gravitational radiation. The waves themselves propagate unimpeded through the universe, passing through matter and radiation with virtually no attenuation, unlike electromagnetic waves. This makes gravitational waves pristine messengers from the most violent cosmic events. The study of these waves has transformed black hole collisions from theoretical curiosities to observable astrophysical phenomena. Detectors like LIGO, Virgo, and the upcoming LISA Space Observatory promise to revolutionize our understanding of the universe, revealing the hidden symphony of spacetime vibrations. The gravitational waves emitted by black hole mergers are not only proof that these cosmic giants collide and merge, but are also invaluable tools that let us listen to the universe's deepest secrets. Merger into a larger black hole. When two black holes collide, one of the most straightforward yet profoundly significant outcomes is their fusion into a single, larger black hole. This process, while it might seem like a simple combination at first glance, involves intricate and extreme physics at the edge of our understanding. The merger is the cosmic culmination of a dance governed by gravity, where two incredibly dense objects spiral inward, distort spacetime, and eventually combine to form a new entity with its own mass, spin, and energy profile. Imagine two black holes, each with their own masses, spins, and orientations, locked in a gravitational embrace. Over millions or billions of years, depending on their environment, they gradually lose energy by emitting gravitational waves, those ripples in spacetime that propagate outward at light speed. This energy loss causes their orbits to shrink and speed up, accelerating the in-spiral phase of the collision. As they draw closer, tidal forces distort each black hole's event horizon, stretching and deforming the invisible boundary that marks the point of no return. The spacetime between them becomes a roiling sea of gravity, waves, and extreme curvature. When the two black holes finally merge, their event horizons coalesce into a single, smooth surface. This merged horizon envelopes a new, larger singularity, the heart of the black hole where density and curvature theoretically reach infinity. The combined mass of this new black hole is not simply the sum of the original masses. A portion of the total mass energy is radiated away as gravitational waves during the merger, typically about 3% to 5%. This radiated energy is enormous, during the brief moments of the merger, it can exceed the luminosity of all the stars in the observable universe combined. The newly formed black hole settles into a stable state through a process called the ring-down phase, where it emits gravitational waves as it vibrates, like a struck bell. This phase encodes valuable information about the final black hole's mass, spin, and the dynamics of the merger itself. Once stabilized, the black hole is described simply by its mass, spin, angular momentum, and possibly charge, in accordance with the no-hair theorem, which states that all other information about the merging bodies is lost to external observers. This fusion process is a cornerstone of modern astrophysics and has been directly observed through gravitational wave astronomy since LIGO's first detection in 2015. The events captured so far involve black holes ranging from a few times the Sun's mass up to dozens of solar masses, confirming theoretical predictions with remarkable accuracy. But the process is not just a merging of masses, it has rich and complex physics underlying it. The spins of the initial black holes influence the dynamics significantly. If both spins are aligned with the orbital angular momentum, the merger proceeds relatively smoothly, but if they are misaligned or anti-aligned, the final black hole may receive a kick, a recoil velocity that can sometimes reach thousands of kilometers per second. This kick can eject the merged black hole from its host galaxy, sending it hurtling through intergalactic space. The merger also influences the astrophysical environment. Gas, dust, and even stars in the vicinity may be disrupted or accreted onto the new black hole, potentially powering luminous electromagnetic signals like jets or flares. Although black holes themselves do not emit light, the environment around them can respond violently, providing possible multi-messenger signals coinciding with gravitational wave detections. From a theoretical standpoint, the merger is an incredible laboratory for testing Einstein's theory of general relativity under conditions of extreme gravity and velocity. The intricate gravitational waveforms predicted by numerical relativity simulations match observations with astonishing precision, confirming our understanding of how spacetime behaves under such intense conditions. The formation of a larger black hole through merger also plays a fundamental role in the cosmic evolution of structure. Stellar mass black holes born from collapsing massive stars can merge repeatedly, growing into intermediate mass black holes, which in turn can be seeds for the supermassive black holes found at the centers of galaxies. Thus, black hole mergers contribute not just to gravitational wave signals but to the grand narrative of galaxy and universe formation. While the classical picture of merger is well established, questions remain at the quantum frontier. What exactly happens to the information encoded in the original black holes? How do quantum effects modify the nature of the singularity? These mysteries motivate ongoing research into quantum gravity and the interplay between general relativity and quantum mechanics. The merger of two black holes into a larger one is a process of monumental cosmic importance. It is a dynamic, energetic transformation where two of nature's most enigmatic objects join to form an even greater force of gravity. This new black hole encapsulates the history of its progenitors in its mass, spin, and the gravitational waves it emitted, standing as both a testament to the power of gravity and a gateway to deeper cosmic secrets. Ring-down phase. The final moments following the merger of two black holes mark one of the most fascinating and subtle phenomena in gravitational physics, the ring-down phase. After the intense and chaotic coalescence of two black holes, the newly formed, larger black hole is far from a static, serene object. Instead, it undergoes a period of oscillations, quivering and vibrating as it sheds excess energy and relaxes into a stable, equilibrium state. This process is crucial for understanding not only the immediate aftermath of the merger, but also the fundamental nature of black holes and the fabric of spacetime itself. When the two black holes merge, their combined event horizon doesn't instantaneously settle into a perfect spherical or oblate shape. Instead, the event horizon is distorted and highly dynamic, stretched by the violent collision and the complex gravitational interactions that precede it. These distortions in spacetime geometry lead to the excitation of specific vibration modes of the black hole, known as quasinormal modes. The gravitational waves emitted during this ring-down phase carry the imprint of these oscillations. The ring-down phase can be likened to the fading sound of a bell after it has been struck. The merged black hole spacetime rings with gravitational wave frequencies characteristic of its mass and spin. These vibrations damp out quickly, with the black hole losing the last vestiges of its asymmetry through gravitational wave emission. Eventually, the black hole settles into a stable Kerr black hole, a solution to Einstein's field equations describing a rotating black hole. One of the profound implications of the ring-down phase is that the frequencies and damping times of these quasi-normal modes depend exclusively on the black hole's mass and spin. This means that by analyzing the gravitational wave signals during ring-down, physicists can determine the properties of the newly formed black hole with exceptional precision. This has been a key method in verifying the predictions of general relativity in the strong field regime. The ring-down phase is generally short-lived, lasting on the order of milliseconds to seconds, depending on the black hole's mass. For stellar mass black holes observed by detectors like LIGO and Virgo, the ring-down signal is brief but intense, appearing as a final decaying chirp in the gravitational wave data. For supermassive black holes, which have masses millions or billions of times that of the Sun, the ring-down phase would last longer and occur at lower frequencies, a regime that future space-based gravitational wave observatories like LISA aim to study. Detecting and analyzing the ring-down is crucial because it provides a unique window into the no-hair theorem, which states that black holes are fully characterized by just a few parameters: mass, spin, and electric charge, the latter usually negligible in astrophysical contexts. If deviations from expected ring-down frequencies or damping times were observed, it could signal new physics beyond general relativity, hint at the presence of exotic compact objects, or even reveal quantum gravitational effects near the event horizon. Beyond confirming black hole properties, the ring-down phase serves as a testbed for alternative theories of gravity. Different models that extend or modify Einstein's theory often predict subtle differences in the ring-down gravitational wave signals. As detection sensitivity improves, the ring-down phase could become a powerful probe of fundamental physics, possibly revealing the quantum nature of spacetime or signatures of hidden dimensions. The ring-down is also intimately connected with the information paradox, a long-standing puzzle about what happens to information that falls into a black hole. While classical theory predicts that the black hole's event horizon and singularity erase all memory of what formed it, some quantum theories suggest that information might be encoded in subtle modifications to the black hole's horizon or emitted during phases like the ring-down. Detecting gravitational wave echoes during or after the ring-down phase has been proposed as a potential signature of such effects, though evidence remains tentative. From a computational standpoint, modeling the ring-down involves solving Einstein's equations numerically and extracting the quasi-normal mode spectra. This requires massive computational resources and sophisticated algorithms, making the ring-down a cutting-edge area of numerical relativity. These simulations have been crucial in predicting what gravitational wave detectors should expect to observe, and in interpreting actual signals. In the grand cosmic narrative, the ring-down phase symbolizes the transition from chaos to order. After the tumultuous merger, the black hole settles into a final, stable configuration that will persist for eons. This phase marks the moment where the dynamic history of two separate black holes is finally unified into a single, coherent object, characterized by its unique mass and spin. In summary, the ring-down phase is a fleeting yet deeply informative episode following black hole mergers. It provides a gravitational wave signature of the newborn black hole's properties, serves as a test of fundamental physics, and holds tantalizing clues to unresolved mysteries in gravity and quantum mechanics. As gravitational wave astronomy matures, studying ring-downs will remain central to unlocking the secrets of the universe's most extreme phenomena. Energy loss via gravitational radiation. One of the most astonishing and profound consequences of black hole mergers is the enormous amount of energy radiated away as gravitational waves, ripples in the very fabric of spacetime itself. Unlike electromagnetic radiation, which includes light and other forms of energy carried by photons, gravitational waves are distortions of spacetime that travel outward at the speed of light, produced by the acceleration of massive objects, especially in asymmetric, violent events like black hole collisions. When two black holes spiral toward each other and finally merge, their combined mass energy does not remain entirely in the newly formed black hole. Instead, up to approximately 5% of the total system's mass is converted directly into gravitational wave energy. This might sound like a small fraction, but in terms of absolute energy, it is staggering. For black holes each tens of times the Sun's mass, this translates to an energy output that briefly outshines all the stars in the observable universe combined, in gravitational wave form alone. To appreciate this, consider the famous event GW150914, the first gravitational wave detection announced by LIGO in 2016. In that merger, about 3 solar masses worth of energy were released as gravitational waves in less than a second. This release equates to roughly 5% of the total system mass, radiated purely as ripples in spacetime, a phenomenon entirely invisible through electromagnetic telescopes but detectable via ultrasensitive instruments. This energy loss is fundamentally linked to Einstein's theory of general relativity. According to Einstein, accelerating masses can cause perturbations in spacetime that propagate outward as gravitational waves. During the in-spiral phase, the black holes orbit each other and lose energy by emitting these waves, causing them to draw closer and accelerate until they collide. The emission becomes dramatically more intense near the merger, where spacetime is warped to its limits. The shape and magnitude of the emitted gravitational waves carry rich information. They encode the masses, spins, and orbital dynamics of the black holes, and the energy radiated reflects the violent nature of their final plunge and merger. Sophisticated numerical relativity simulations model these processes, solving Einstein's equations on supercomputers to predict the waveforms we detect. The peak gravitational wave luminosity during merger surpasses any known astrophysical event, briefly reaching more than 10 to the power of 56 ergs per second, orders of magnitude greater than the combined electromagnetic output of all galaxies. This extreme burst of energy, while not directly observable through light, dramatically alters the space-time geometry around the black holes and carries information across the cosmos. Importantly, the energy carried away by gravitational radiation directly reduces the mass of the resulting black hole compared to the sum of the original masses. This mass difference is the missing energy radiated away. The more asymmetric or dynamic the merger, such as with misaligned spins or unequal masses, the larger the gravitational wave emission can be, and consequently, the larger the energy loss. Energy loss via gravitational radiation is not only critical to the merger dynamics but also shapes the final velocity and spin of the remnant black hole. As gravitational waves carry momentum away asymmetrically, the merged black hole can receive a recoil, or kick, propelling it through space at speeds that can sometimes exceed thousands of kilometers per second. Such a kick can eject the black hole from its host galaxy or star cluster, influencing cosmic structure evolution. Beyond astrophysics, the detection of gravitational waves and the measurement of their energy content open new windows into fundamental physics. They allow scientists to test general relativity under extreme conditions, search for deviations that might hint at new physics, and probe the nature of spacetime itself. This energy loss also has implications for the life cycle of black holes in the universe. Repeated mergers and gravitational wave emissions can gradually influence the mass distribution and growth of black holes across cosmic time, contributing to the population of intermediate and supermassive black holes. In the broader cosmic context, energy loss through gravitational waves from black hole mergers is a key mechanism by which energy and information propagate through the universe. Unlike light, gravitational waves can pass unimpeded through matter, traveling billions of light years and delivering pristine signals from the universe's most cataclysmic events. As gravitational wave observatories improve, they will continue to measure the energy radiated in these cosmic collisions with ever greater precision, enriching our understanding of black holes and the energetic processes that shape our universe. Spin alignment theory. In the cosmic ballet of black hole collisions, one of the subtler yet profoundly influential factors is the orientation of each black hole's spin, essentially, how each black hole's axis of rotation is aligned relative to the other and to the orbital plane in which they spiral toward each other. This concept, known as spin alignment theory, plays a critical role in determining the intricate dance steps of the merger, the properties of the resulting black hole, and the nature of the gravitational waves emitted. Black holes, like planets and stars, can spin, often at speeds close to the speed of light at their event horizons. The direction and magnitude of these spins are fundamental parameters that influence the dynamics of their interactions. When two spinning black holes approach one another, their spins can be aligned, anti-aligned, or misaligned in complex ways relative to their mutual orbital angular momentum. If the spins are aligned, meaning the rotation axes of both black holes point in roughly the same direction as their orbital axis, the merger tends to be more orderly, and the final black hole typically ends up with a higher spin rate. This aligned spin configuration causes the black hole's individual angular momenta to add constructively, making the remnant spin faster. Conversely, if the spins are anti-aligned, pointing opposite to the orbital axis, or misaligned at some angle, the merger becomes far more complicated. The spins can interact through spin-orbit and spin-spin coupling effects, causing the black holes to wobble or precess during their in-spiral. This precession affects the shape and phase of the gravitational waves emitted, producing modulations that can be detected by sensitive observatories. Misaligned spins also tend to reduce the final spin of the merged black hole because parts of the individual spins can partially cancel out each other's angular momentum. This leads to a final black hole that may spin more slowly or even have its spin axis tilted relative to the original orbital plane. These spin interactions significantly influence the dynamics of the merger, affecting how the black holes spiral together, how much energy and angular momentum are radiated away as gravitational waves, and the distribution of momentum carried off asymmetrically. The resulting kick velocity imparted to the merged black hole depends in large part on spin orientation. Certain spin configurations can lead to especially large recoil speeds, potentially ejecting the remnant from its host environment. Spin alignment also carries clues about the history of the black holes. For instance, black holes formed from the collapse of massive stars in a binary system are expected to have spins that are more aligned due to the shared angular momentum of their progenitor stars. On the other hand, black holes that formed independently and later encountered each other in dense stellar environments like globular clusters may have randomly oriented spins. Studying the spin orientations through the gravitational waves produced during merger events has become a crucial tool for astrophysicists. By analyzing waveform patterns and their modulations, scientists can infer the spin magnitudes and directions, providing insights into black hole formation channels and the environments in which mergers occur. The spin alignment theory is also deeply intertwined with testing general relativity in the strong field regime. Accurate models of spin interactions are necessary for predicting gravitational waveforms, which are then matched to observed signals. Any deviations might hint at new physics or help refine our understanding of gravity's behavior near black holes. From a computational perspective, modeling the complex spin dynamics requires advanced numerical relativity simulations that incorporate general relativistic effects, spin precession, and nonlinear interactions. These simulations guide the interpretation of gravitational wave data and improve the precision of black hole parameter estimates. Furthermore, the spin alignment influences the stability and structure of the final event horizon. The spin rate affects the shape of the horizon, typically making it oblate, flattened at the poles, and altering the ergosphere, a region outside the horizon where frame dragging effects are strongest. This has implications for processes like the extraction of rotational energy via mechanisms such as the Penrose process or Blandford's Najek effect. In summary, the orientation and magnitude of black hole spins are not mere details but central players in the drama of black hole mergers. They dictate the merger's dynamical choreography, shape the gravitational wave signals we detect, determine the final black hole spin and recoil, and provide critical clues about the astrophysical origins of these enigmatic objects. Kick velocity. When two black holes collide and merge, the newly formed black hole does not always remain exactly where the original pair came together. Instead, it can receive a powerful kick, propelling it through space at extraordinary speeds. This phenomenon, known as kick velocity, arises from the asymmetric emission of gravitational waves during the merger, a subtle but profound effect that shapes the destiny of black holes and influences the cosmic landscape. The source of the kick lies in the fundamental principle of conservation of momentum. Just as a rocket propels itself by expelling gas backward, the newly merged black hole can recoil when gravitational waves carry momentum away unevenly. If the emission of gravitational waves during the final stages of the merger is perfectly symmetric, the merged black hole would stay put. But often, the spins, masses, and orbital configurations of the two original black holes cause the waves to be emitted more strongly in one direction, pushing the remnant in the opposite direction. This recoil velocity can be incredibly high. Depending on the parameters of the merging black holes, their mass ratios, spin magnitudes, and spin orientations, kicks can range from a few tens of kilometers per second to several thousand kilometers per second. The upper range is so extreme that it can propel the merged black hole entirely out of its host galaxy, sending it hurtling through intergalactic space. One particularly fascinating aspect is the role played by spin. When the spins of the merging black holes are misaligned or unequal, they generate complex, precessing gravitational wave patterns. These asymmetries are key contributors to significant kicks. In some scenarios, if the spins are oriented in opposite directions within the orbital plane, the merged black hole can be flung away at velocities surpassing 5,000 km per second, enough to escape even the gravitational grip of the largest galaxies. This phenomenon was first predicted through detailed numerical simulations solving Einstein's equations for binary black hole mergers. Early theoretical work showed that the gravitational wave emission patterns were not always balanced and that resultant recoil velocities could be substantial. Subsequent computer models refined these predictions, confirming the possibility of such powerful kicks. The astrophysical implications of kick velocity are enormous. If a supermassive black hole at the center of a galaxy receives a large enough kick, it might be ejected from the galactic nucleus, leaving the galaxy temporarily or permanently without its central black hole. This displacement could affect the galaxy's evolution, star formation rates, and the dynamics of surrounding matter. Observationally, this might manifest as rogue black holes wandering in intergalactic space or as galaxies missing their expected central supermassive black holes. Moreover, kicks influence the growth and demographics of black holes across the cosmos. Smaller black holes formed through stellar collapse might also experience kicks during mergers, affecting their retention in star clusters or their ability to form larger black holes through repeated mergers. The distribution of kick velocities helps shape the population of black holes we observe. Gravitational wave detectors like LIGO and Virgo can provide indirect evidence of kicks by analyzing the subtle shifts and patterns in the waveforms. For example, asymmetries in the signal's amplitude or phase can hint at the recoil magnitude and direction. Although we cannot directly see the kick, the gravitational wave data combined with electromagnetic observations may reveal clues about displaced black holes or active galactic nuclei moving unexpectedly. In some extraordinary cases, the kick could produce observable phenomena such as relativistic jets or displaced quasars, if the black hole carries along its accretion disk or jet-producing structures as it is ejected. Searching for such signatures is an active area of astronomical research. From a theoretical perspective, the kick velocity exemplifies the remarkable interplay between general relativity, astrophysics, and high-performance computation. Predicting kicks requires sophisticated numerical relativity simulations that model the nonlinear dynamics of spacetime curvature, spinning black holes, and gravitational wave emission. These simulations must account for complex initial conditions, including spin magnitude, direction, and mass asymmetry. In summary, kick velocity reveals that black hole mergers are not just spectacular but can be surprisingly messy events with profound consequences. The merged black hole can be launched on a cosmic journey by asymmetric gravitational wave emission, influencing galaxy evolution, black hole demographics, and our understanding of fundamental physics. This cosmic recoil underscores the dynamic, interconnected nature of our universe, where even the most massive, enigmatic objects are subject to the subtle yet powerful laws of motion. No-hair theorem. One of the most elegant and profound principles in black hole physics is the no-hair theorem, a concept that captures the simplicity underlying the seemingly chaotic and violent process of black hole mergers. Despite the complexities involved when two black holes collide, warp spacetime, and unleash torrents of gravitational waves, the ultimate product of this cosmic event, the final merged black hole, is remarkably simple in its defining characteristics. According to the Noether theorem, a black hole can be completely described by just three externally observable parameters: mass, spin, angular momentum, and electric charge. This means that all other information about the original black holes, the so-called hair, is lost to outside observers, encapsulated only by these three quantities. The phrase, "no hair," was coined by physicist John Archibald Wheeler in the 1960s, metaphorically suggesting that black holes have no distinguishing features beyond these basic properties, unlike other physical objects which might have complex surface features or hair. This idea embodies the astonishing fact that black holes, despite their complexity and the diverse matter that formed them, reduce to such a simple description. When two black holes merge, the individual identities, the detailed structure, the complex history, the distributions of matter and radiation swallowed, are erased behind the event horizon. The event horizon acts like a one-way membrane. Anything crossing it, including information about the original configurations, cannot escape back into the universe. What remains visible from the outside is the mass, which sums roughly from the two original black holes minus the energy radiated away, the net spin, which depends on how the original spins combined, and the net electric charge, which in astrophysical contexts is generally negligible because charges tend to neutralize quickly. The Noether theorem is closely tied to the nature of the event horizon and the underlying mathematics of Einstein's field equations in general relativity. The solutions describing black holes, such as the Kerr-Newman metric, demonstrate that the external gravitational and electromagnetic fields can be entirely characterized by mass, spin, and charge. This means that two black holes with identical values of these parameters are indistinguishable from the outside, no matter their formation history or internal complexity. This simplicity has profound implications for our understanding of the universe. It suggests a universality and robustness in black hole physics. After the chaos of a merger, the resulting black hole forgets the details, settling into a stable state defined only by these parameters. This outcome is a form of cosmic censorship and elegance in nature's laws. The Noether theorem also raises deep and ongoing questions related to the information paradox. According to quantum theory, information should never be destroyed, yet the Noether theorem implies that all distinguishing information about the matter that formed or fell into a black hole is lost from the perspective of an outside observer. Reconciling this with quantum mechanics remains one of the great challenges in theoretical physics. Testing the Noether theorem observationally is an exciting frontier in astrophysics and gravitational wave astronomy. Precise measurements of the gravitational waves emitted during the ring-down phase of a black hole merger provide a way to verify if the remnant black hole behaves exactly as predicted, characterized only by mass, spin, and charge. Any deviations could point to new physics beyond general relativity, such as exotic fields, quantum effects, or alternative gravity theories. Thus far, observations from LIGO, Virgo, and other detectors have found no evidence contradicting the Noether theorem, strengthening the confidence that this principle holds in nature. Yet the quest continues, with future more sensitive instruments like LISA, Laser Interferometer Space Antenna, promising to probe black holes with unprecedented precision. In summary, the Noether theorem reveals a stunning simplicity behind the apparent complexity of black hole mergers. Regardless of the intricate dance leading up to the collision or the violent emission of gravitational waves, the final black hole is distilled down to just mass, spin, and charge. No other hair remains. This insight not only deepens our understanding of black holes but also illuminates profound questions about information, quantum gravity, and the fundamental fabric of reality. Event horizon stability. As two black holes spiral closer together in a death dance of unimaginable gravity, the one feature that defines them both, the event horizon, becomes the stage for one of the most elegant, yet mysterious processes in the cosmos. The event horizon, a boundary beyond which nothing, not even light, can escape, is more than just a region of no return. It is a manifestation of space-time geometry itself, shaped entirely by mass, spin, and energy. And during a merger, these horizons don't shatter or burst, they merge, just as the black holes do. What unfolds is a seamless transformation governed by the stability of space-time, culminating in the birth of a new, larger horizon. This process is encapsulated by what physicists call event horizon stability. To the outside observer, the merger of event horizons appears smooth, continuous, and causally ordered. It doesn't produce any visible tear or discontinuity in space-time. There is no visible edge, explosion, or sharp boundary. Instead, the horizons of the two black holes coalesce into a larger, encompassing horizon that gently molds itself around the new, combined singularity. This new horizon grows rapidly and stabilizes in a dynamic yet predictable fashion. It's as if two soap bubbles merge into a bigger bubble, not violently, but fluidly, respecting the constraints of spacetime and causality. The mathematics of general relativity ensures this stability under most conditions. When two black holes merge, the Einstein field equations guide the warping and reshaping of spacetime, and consequently, of the horizon itself. In technical terms, the event horizon is a null surface generated by light rays that just fail to escape. These light rays form a smooth surface, and when two black holes come together, the congruence of these rays reforms without disruption. The resulting surface is continuous and well-defined, extending out to encompass the area around the newly formed singularity. One of the keys to understanding this lies in cosmic censorship and causal structure. The cosmic censorship conjecture suggests that singularities, points of infinite density at the heart of black holes, are always hidden behind event horizons. This preserves causality and ensures that we never observe the breakdown of physics directly. During a merger, this principle continues to hold. The new event horizon forms early enough in the process to enshroud any potentially exposed singular behavior. There's no naked singularity, no breakdown of predictability. The causal structure, the orderly sequence of cause and effect, remains intact. Numerical simulations of black hole mergers provide striking visualizations of this stability. As the black holes spiral inward and collide, their individual horizons distort, stretching and flattening due to tidal forces, but they never rupture. Just before contact, a common apparent horizon forms, enveloping both black holes. This is a precursor to the global event horizon, which encompasses the final black hole. After the collision, the new horizon oscillates, like a struck bell, before settling into a perfect sphere or oblate spheroid, depending on the spin. This phase is what's known as the ring down, another reflection of the smoothness and stability of the event horizon. The notion of horizon area increase also plays a pivotal role. According to the second law of black hole thermodynamics, the area of a black hole's event horizon can never decrease. When two black holes merge, the total area of the new event horizon is always greater than or equal to the sum of the areas of the original two. This thermodynamic law, surprisingly similar to the second law of entropy in conventional physics, reinforces the idea that black hole mergers lead to a stable, larger configuration, not fragmentation or destruction. In quantum gravity research, this stability of the horizon poses deep questions. For example, if black holes are more than just smooth surfaces, if they have microstates or quantum structures as posited by string theory or loop quantum gravity, then what happens during horizon merger? Do the microstates reconfigure into a new set of quantum degrees of freedom smoothly, or is there a chaotic quantum reshuffling under the surface? Some theories like the Fuzzball proposal or Firewall hypothesis challenge the classical picture, suggesting the process may not be as placid at the microscopic level. However, at macroscopic, classical scales, the event horizon retains its smooth, continuous nature. Moreover, event horizon stability isn't merely a theoretical prediction, it's part of the growing observational frontier. The gravitational waves emitted during the merger reflect the behavior of spacetime itself. If the horizon were unstable or broke apart during merger, these waves would show irregularities, perhaps echoes, distortions, or chaotic signals. Instead, the waveforms detected by LIGO and Virgo match the expectations of stable, coherent mergers. They exhibit clean transitions from in-spiral to merger to ring down, indicating that spacetime is following the rules of stability dictated by general relativity. Another implication of event horizon stability is the preservation of black hole uniqueness. The final black hole settles into a stationary state defined solely by its mass and spin, and charge, though astrophysical black holes are thought to be neutral. There is no memory of the complex merger path once the horizon stabilizes. This, settling down, ensures predictability and reinforces the elegance of the no-hair theorem described earlier. Ultimately, event horizon stability tells us that even in the most violent and energetic processes in the universe, black hole collisions, there is a deep and enduring order. The laws of physics hold firm. Space-time, rather than tearing apart, weaves itself into a new configuration. The event horizon, far from being a destructive edge, acts as a dynamic yet stabilizing boundary, evolving gracefully through the collision and aftermath. This segment of black hole physics reminds us that the universe, while chaotic in appearance, is underpinned by mathematical consistency. The event horizon, intangible yet definable, represents not only a barrier to escape, but a commitment to cosmic stability. Through the lens of event horizon stability, black hole mergers become not cosmic catastrophes, but harmonious transitions between states of gravitational order. Singularity merger. Deep within every black hole lies the most enigmatic and paradoxical feature of all, the singularity. It is the ultimate point of collapse where density becomes infinite, spacetime curvature grows without bound, and all known laws of physics cease to apply. General relativity predicts that singularities form as the final fate of massive objects that collapse under their own gravity beyond the critical limit. And yet, it offers no description for what actually happens at that point. When two black holes merge, it's not just their horizons that combine, it is also their singularities. This process, known as singularity merger, remains one of the most profound mysteries in theoretical physics. Unlike the event horizon, which can be mathematically and visually modeled and observed indirectly through gravitational waves, singularities are forever hidden from view. They lie beneath the event horizon, completely shielded from the external universe. What makes the merger of singularities even more compelling is that this process occurs entirely within that hidden realm. We can only theorize about it using equations and simulations that are stretched to their breaking point in regions where quantum effects, gravity, and spacetime all collide in extreme ways. In a classical description using general relativity, when two black holes begin to merge, their event horizons approach and eventually fuse. But deep inside, the central singularities, the points where matter has collapsed to infinite density, remain separated for a brief time. As the merger progresses and the horizons become one, a gravitational bridge of spacetime stretches between the two singularities. These singularities, being geodesic boundaries in spacetime, eventually converge. When this happens, they fuse into a single, larger singularity that reflects the combined mass and momentum of the original black holes. From a relativistic standpoint, this process is governed by the inexorable pull of gravity. The extreme spacetime curvature at the core of each black hole distorts even further during the final stages of coalescence. The geometry around the singularities becomes unstable and is violently reshaped. As the surrounding event horizon stabilizes, the singularity at the heart of the new black hole is no longer a simple point, but a massively more energetic and distorted spacetime entity. In spinning black holes, the singularity may even take on a ring shape, a so-called ring singularity, depending on the angular momentum involved in the merger. Yet here lies the problem. Singularities are unphysical in the sense that they break the equations used to describe them. They are places where general relativity yields infinite values and ceases to be predictive. This breakdown strongly implies that general relativity is an incomplete theory, especially in extreme regimes like black hole interiors, and that a more fundamental theory, likely involving quantum gravity, is needed to describe what truly happens during a singularity merger. In quantum theories, such as loop quantum gravity and string theory, the idea of a singularity is often replaced by a quantum object or structure where the infinite density is somehow avoided. For instance, loop quantum gravity suggests that spacetime itself is made up of discrete chunks, quantized loops of space, which might prevent infinite curvature. Instead of a singularity, the core of a black hole could be a quantum bounce region where matter is compressed to near Planckian scales but never truly collapses to a point. If two such quantum cores meet, the merger might involve the unification of two complex networks of quantum spacetime geometry rather than classical infinities. Alternatively, in string theory, the singularity may be replaced by a configuration of vibrating strings or branes that encode the quantum information of the collapsed matter. The merger in this context could be seen as a reconfiguration or entangling of two bundles of strings into a new, more massive, and complex string configuration. This also opens the door to speculative but fascinating ideas such as fuzzballs or even emergent spacetime, where the entire black hole interior is a manifestation of quantum information interactions. Still, even with these theoretical models, we cannot yet say with certainty what the singularity is or what exactly happens when two of them merge. The only certainty is that our current physical laws are inadequate at those scales, and the singularity merger represents a boundary of knowledge, a place where a unified theory of quantum gravity must one day provide answers. One further implication of the singularity merger ties into the information paradox. If singularities are where information vanishes, then the merger might represent a kind of compounded information loss, yet quantum theory tells us information cannot be destroyed. Some researchers have speculated that whatever happens in the singularity merger, it must involve a process that retains or re-encodes all quantum information from the two original black holes. The nature of this encoding, whether on the event horizon as per the holographic principle, or within the core structure as quantum data, is still a matter of intense debate. And while we can't directly observe the merger of singularities, we can detect the indirect gravitational echoes and behaviors in the ring-down phase of black holes. If these contain subtle anomalies, they might offer hints about what lies beyond the veil. So far, gravitational wave observations have been consistent with classical expectations, but as detection methods become more precise, we may one day witness anomalies that point toward quantum processes deep inside the black hole. In all, the singularity merger is a boundary event, not just in spacetime, but in physics itself. It represents the frontier where our theories bend, crack, and hint at something deeper and more fundamental. Two cosmic hearts of infinite density colliding and merging into one. It is not simply the addition of mass or the reshaping of spacetime, but potentially the birth of a new kind of entity entirely, waiting for future physics to understand. Cosmic censorship conjecture. One of the most haunting and profound questions in the study of black holes and spacetime is this: what if we could see a singularity? That is, what if the veil of the event horizon failed, and the raw, unfiltered chaos of a gravitational singularity was exposed to the universe? According to general relativity, singularities, those regions of infinite density and curvature, should form in gravitational collapse. But there's a deep discomfort in allowing them to be visible, because singularities are places where physics, as we know it, breaks down. This concern gave rise to one of the most important and controversial ideas in gravitational theory, the cosmic censorship conjecture. Proposed by Roger Penrose in 1969, the cosmic censorship conjecture essentially states that all singularities formed by gravitational collapse must be hidden behind event horizons. In other words, nature censors the most extreme features of spacetime from the outside universe. It forbids the formation of naked singularities, singularities exposed without a surrounding event horizon. This conjecture has both a weak and a strong version, but in the context of black hole collisions, it's the weak version that's most relevant. It insists that any singularity created by the merger of two black holes will remain cloaked behind a newly formed event horizon, preserving cosmic order. During a black hole collision, this principle is put to a terrifying test. As the two titanic objects spiral inward and their event horizons begin to merge, their singularities are dragged closer and closer together. The spacetime curvature near each one grows extreme. In a naive scenario, one might imagine that as the singularities combine, their gravitational fields might momentarily break through the horizon, exposing the singularity, if only for a fraction of a second. But according to cosmic censorship, this does not happen. The event horizon reshapes and stretches in such a way that it always envelopes the chaotic inner region, forming a barrier through which no information can escape. This cloaking is not just a visual shroud, it's a causal barrier. Events that happen inside the horizon cannot influence anything outside it. Thus, the singularity remains completely divorced from the external universe. The merger does not produce any observable breakdown of causality or determinism in the cosmos, because the singularity's influence is always hidden behind the event horizon. Cosmic censorship preserves the predictability of physics outside the black hole, allowing observers to trust that the fundamental equations remain intact beyond that boundary. The importance of cosmic censorship in the merger process cannot be overstated. If it were violated, if even a tiny portion of a singularity were to be revealed, the consequences could be catastrophic for theoretical physics. Naked singularities would allow observers to see regions where the known laws of physics completely break down. The concept of determinism, where cause leads to effect, would no longer apply. Future evolution of systems would become unpredictable. Time, causality, and information could all behave in incomprehensible ways. Some speculative theories suggest that under very rare or exotic conditions, naked singularities might actually form. For example, if a rotating black hole were spinning close to its theoretical maximum, the Kerr limit, and a collision injected just the right amount of angular momentum or asymmetry, the resulting object could temporarily exceed the critical spin threshold. In this hypothetical case, the centrifugal force could overcome gravity at the horizon, pulling it apart and exposing the core. This would create a brief window where the singularity is visible to the external universe. But even in these extreme scenarios, most physicists believe that cosmic censorship remains intact, that some stabilizing mechanism steps in to restore the horizon or prevent the singularity from fully emerging. Numerical simulations of black hole mergers support the cosmic censorship hypothesis. Sophisticated models using supercomputers show that even when black holes of vastly different sizes collide, or when their spins are wildly misaligned, the resulting spacetime always evolves in a way that maintains an enclosing event horizon. The newly formed black hole quickly settles into a stable configuration with no signs of singularity exposure. These simulations lend powerful, albeit indirect, support to the conjecture. The cosmic censorship conjecture also carries deep implications for the information paradox and the potential unification of quantum mechanics and general relativity. If singularities are always hidden, it may be possible that all information about matter falling into a black hole is somehow preserved on the horizon, as suggested by the holographic principle, rather than being lost to a visible singularity. If, however, cosmic censorship failed, and we could see singularities directly, the nature of information loss might become far more chaotic and unmanageable, possibly implying the breakdown of unitarity in quantum mechanics. But for all its philosophical and theoretical weight, cosmic censorship remains, to this day, an unproven conjecture. There is no formal proof that singularities must always be hidden, though every physical process we've been able to model so far supports the idea. It may be that the universe is more well-behaved than it needs to be, shielding us from its most violent truths. Or perhaps the laws of physics themselves enforce this boundary, rejecting initial conditions that would otherwise expose the singularity. In the context of black hole mergers, cosmic censorship is the quiet guardian that ensures the rest of the universe remains stable and knowable. Without it, we would be forced to confront not just the unimaginable density of singularities, but the collapse of our entire framework for understanding cause and effect. Black holes are already mysterious enough, but cosmic censorship is what keeps them from becoming truly chaotic monsters in the cosmic zoo. Information paradox. Among all the mysteries surrounding black holes, perhaps none is more profound, and more philosophically troubling, than the black hole information paradox. At its core, this paradox challenges our deepest assumptions about how the universe works, and it does so at the crossroads of quantum mechanics, general relativity, and thermodynamics. The paradox becomes especially relevant when two black holes collide and merge, raising a deeply unsettling question: what happens to the information contained in each of the original black holes? Let's break down why this is such a colossal issue. In classical physics, information about the state of a system, its particles, energy, and configuration, is never truly destroyed. Even if something is transformed beyond recognition, like burning a book, the information about the book is still technically present in the arrangement of smoke particles, ash, and energy. In quantum mechanics, this idea becomes sacred. Unitarity, a foundational principle, demands that the evolution of any closed quantum system must be reversible. In simple terms, you should always be able to, at least in theory, rewind the universe and retrieve the original state of any system. Now enter the black hole. When something, be it matter, light, or even complex structures, falls past the event horizon, it's gone from the observable universe. We can no longer interact with or retrieve it. As the black hole ages, it slowly evaporates via Hawking radiation, which is theorized to be random and thermal, carrying no specific information about what fell in. Eventually, the black hole might shrink to nothing, vanishing completely from the universe. But then, where did the information go? Was it destroyed? This is the essence of the black hole information paradox, first highlighted by Stephen Hawking in the 1970s. According to his calculations, black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation seems to be entirely featureless, lacking any encoding of the infalling material's details. If this is true, then the information about what formed the black hole, stars, planets, even civilizations, would be lost forever. This directly violates quantum unitarity and calls into question the consistency of the laws of physics. When two black holes collide, this issue becomes even more tangled. Each original black hole carries its own internal information, the record of everything it has swallowed. When they merge, the new, larger black hole should, according to classical theory, have an even more complex internal configuration. But outwardly, the result seems strangely simple. Thanks to the Noether theorem, the final black hole is fully described by only three properties: mass, spin, and charge. All other information about the merging black holes, including the exact matter content and internal quantum states, appears to be lost behind the event horizon. Even if we could somehow rewind and observe the merger from every possible external angle, we'd still only see this reduced, sanitized version of events. So the paradox deepens. The merger of black holes compresses two informationally rich regions into one, and we're left with a seemingly featureless object. Then, if that final black hole evaporates over trillions of years via Hawking radiation, all that composite information, encoded in the swirling chaos of spacetime and matter, seems to dissolve into nothing. This contradiction between the demands of quantum theory, which says information must be preserved, and the predictions of black hole thermodynamics, which suggest it can be lost, has driven decades of theoretical work, spawning a multitude of proposed solutions. One idea is that Hawking radiation is not actually random. According to some interpretations, subtle quantum correlations are encoded within the radiation, so that if one had an unimaginably precise measurement apparatus, they could reconstruct the original information from the emitted particles. This view suggests that information does leak out, just extremely slowly and in a scrambled form. In the context of a black hole merger, this would mean that while the new black hole seems to have hidden the internal information, it will eventually emit it over eons through complex quantum patterns in the radiation. Another line of thinking invokes the holographic principle. This radical idea, inspired by string theory and championed by physicists like Gerard T. Hooft and Leonard Susskind, proposes that all the information contained within a black hole is actually stored on its two-dimensional event horizon, not in its three-dimensional volume. The horizon acts like a kind of cosmic hard drive, encoding the entire history and structure of the matter it has consumed. In a merger, the two horizons would combine and re-encode all prior information onto the surface of the new, larger black hole. If this is true, the information isn't lost, it's just rearranged and hidden in plain sight, projected onto the horizon in a form we cannot yet decipher. More speculative theories include the Firewall hypothesis, which suggests that rather than a smooth event horizon, The boundary of a black hole might be a searing wall of high-energy quantum interactions that obliterate information as it falls in. This view prioritizes the safety of quantum unitarity over the traditional smoothness of spacetime, but it also leads to its own paradoxes, particularly the breakdown of the equivalence principle, a core tenet of general relativity. If firewalls exist, then black hole mergers would involve the violent collision of these walls, potentially disrupting the information in unpredictable ways. There are also quantum gravity approaches, such as loop quantum gravity, that propose black holes don't end in singularities at all, but in Planck scale structures or quantum bounces, where information is preserved in a new form or even expelled into other regions of the universe. In a merger scenario, such models would mean that rather than fusing two classical singularities into one, the process involves a highly complex quantum interaction that could preserve or redistribute the information into microscopic structures or even hidden dimensions. String theory offers another model, the Fuzzball proposal, which eliminates the singularity entirely and instead describes black holes as massive, tangled networks of strings, each configuration corresponding to a particular microstate. When two fuzzball-like black holes collide, the result is a new fuzzball with an even richer internal structure. This theory preserves information by allowing each unique configuration of the black hole to represent a valid quantum state, effectively resolving the paradox in a radically different way. And there's the mind-bending possibility of quantum entanglement across horizons. This concept, linked with the ER equals EPR conjecture, suggests that entangled particles falling into black holes remain connected with the external universe through tiny wormholes. In a merger, this entanglement might persist or rewire, allowing the information to subtly escape or be retained across dimensions. Despite all these attempts, no single solution has gained universal acceptance. The information paradox remains open, a burning question at the heart of modern physics. The merger of two black holes doesn't solve the paradox, it magnifies it. It takes the unknown content of two invisible realms and merges them into a single object that hides even more, giving rise to deeper questions. Where did the information go? Is it still there, scrambled across the horizon, or is it irrevocably lost? Will Hawking radiation eventually tell the story, or must we invent an entirely new physics to understand? What is certain is this. Every black hole merger we detect through gravitational waves, every ripple in spacetime that whispers of ancient collisions, is also a message from a cosmic vault, locked tight with secrets we have yet to comprehend. The black hole information paradox isn't just a problem, it's a cosmic invitation, a challenge issued by the universe to uncover its most hidden truths. Firewall hypothesis. Among the most unsettling and controversial ideas to emerge from modern black hole theory is the firewall hypothesis, a concept that, if proven true, would shake the very foundation of Einstein's general relativity and our understanding of the smooth, continuous nature of spacetime. The hypothesis proposes that a violent, ultra-energetic boundary, known as a firewall, may form at or near a black hole's event horizon, annihilating anything that attempts to cross. When considering black hole collisions, the potential interaction of two such firewalls becomes even more dramatic, suggesting the formation of immense barriers of seething quantum energy that could rewrite the rules of physics under extreme conditions. Let's unpack this. In classical general relativity, if you were to fall into a sufficiently large black hole, you wouldn't notice anything remarkable as you passed the event horizon, at least not immediately. This assumption stems from the equivalence principle, a cornerstone of Einstein's theory. It posits that, locally, the laws of physics are the same in all freely falling reference frames. So, if the black hole is massive enough, tidal forces at the event horizon would be negligible, and you could cross the boundary without encountering any strange physical effects, until much deeper within. However, the firewall paradox, first proposed in 2012 by physicists Ahmed Amhiri, Donald Maroff, Joseph Polchinski, and James Sully, collectively referred to as AMPS, challenges this serene vision. Their argument arises from an attempt to solve the black hole information paradox by preserving unitarity, the idea that information in a quantum system is never truly lost. But when you combine three deeply rooted principles, unitarity, the equivalence principle, and the concept that information is not duplicated, a tenet of quantum mechanics known as the no-cloning theorem, you end up with a contradiction. To resolve it, the AMPS proposal suggested that something has to give, and the most expendable candidate, they argued, is the equivalence principle. That means, instead of smoothly gliding through the event horizon, an infalling observer would encounter a firewall, a wall of high-energy quantum particles created by the breakdown of quantum entanglements at the horizon. These entanglements are essential for preserving unitarity during black hole evaporation, particularly in the emission of Hawking radiation. If they are severed, a huge burst of energy could be released, a firewall. Now, imagine this in the context of two black holes spiraling toward one another in a titanic merger. Each black hole could, in theory, possess its own firewall. As the two event horizons approach and begin to merge, their firewalls would also encounter each other. But what happens when two surfaces of pure quantum fire collide? In one possibility, the firewalls may annihilate each other, releasing an explosive torrent of radiation that could, in theory, be detectable, though no such emissions have ever been observed. Alternatively, they could combine into a super firewall, wrapping the newly formed event horizon in an even more destructive sheath of quantum fury. This hypothetical firewall would surround the final black hole like a shell of death, disintegrating anything that attempted to enter. If this model is accurate, it would radically alter our understanding of what a black hole merger really is. Instead of a smooth gravitational ballet ending in the graceful formation of a new event horizon, it would be a chaotic quantum apocalypse. Two regions of space-time slamming together, tearing apart their own internal quantum correlations and blasting the area with energy far beyond anything imagined in classical physics. Of course, such predictions remain highly speculative. The firewall hypothesis is deeply controversial because it conflicts with relativity's insistence on smooth horizons. Many physicists remain skeptical of the idea, hoping that some new theory, perhaps from quantum gravity or string theory, will reconcile the paradox without resorting to such extreme measures. Another wrinkle in this debate is the nature of Hawking radiation itself. If radiation emitted from a black hole carries information, as some recent models suggest, then the need for a firewall diminishes. In this picture, the horizon remains smooth, and information leaks out gradually via entangled quantum states, no searing wall required. But this solution remains elusive and hotly debated. In the context of black hole mergers, the firewall hypothesis brings up other fascinating questions. Would the formation of a firewall affect the shape or spectrum of gravitational waves emitted during the collision? Could future detectors, even more sensitive than LIGO and Virgo, pick up subtle anomalies, wave echoes, or unexpected frequency shifts that hint at exotic quantum events like firewall formation? Some researchers believe so, and these ideas have sparked numerous theoretical papers exploring the possibility of gravitational wave echoes as signals of non-classical horizons. There's also the consideration of quantum entanglement entropy. If firewalls form due to the loss of entanglement between outgoing and infalling radiation, how does that process unfold during a merger? As the two black holes coalesce, do their respective entangled systems combine harmoniously, or do they clash and fragment, producing decoherence on a cosmic scale? Could the act of merging, with all its violence and energy, be enough to reset the entanglement structure, thereby preventing firewall formation in the final black hole? Or, in an even more exotic twist, perhaps firewalls are temporary. During the intense conditions of a merger, they might flare up briefly, only to collapse as the new horizon stabilizes and restores its entanglement balance. In this view, the firewall is more of a transient event, a flare of quantum energy sparked by the merger's extreme dynamics, rather than a permanent barrier. And there's a philosophical layer to this debate. Firewalls challenge the notion of black hole complementarity, a principle that allows different observers to have different but non-contradictory descriptions of the same black hole. For an external observer, the black hole appears to evaporate gradually, leaking information. For an infalling observer, space-time remains smooth until they reach the singularity. Firewalls throw a wrench in this harmony by insisting that everyone sees the same violent boundary. If they exist, they strip away the elegance of complementarity and force us to confront a hard truth. Our universe may not be as forgiving, or as smooth, as Einstein hoped. The Firewall hypothesis sits at the crossroads of some of the most heated debates in modern theoretical physics. It pits general relativity against quantum mechanics in a battle of principles, and the outcome may very well redefine our view of space-time, information, and reality itself. Black hole mergers, with their titanic energies and violent fusions of horizons, may be the ultimate testing grounds for these ideas. Whether firewalls are real, and whether their effects can be seen in the ripples of spacetime we observe, remains one of the most thrilling and chilling questions we face. Hawking radiation disruption. In the twilight zones of astrophysical theory, few concepts are as iconic and as mysterious as Hawking radiation. Proposed by Stephen Hawking in 1974, this phenomenon bridged the vast chasm between quantum mechanics and general relativity, suggesting that black holes are not entirely black after all. They slowly evaporate by emitting faint thermal radiation, eventually disappearing over incomprehensibly long timescales. But when two black holes collide in a violent cosmic merger, what becomes of this slow trickle of quantum decay? Could the process of Hawking radiation be altered, reset, or even disrupted entirely by the enormous energies and space-time warping of such a collision? To understand this question, we must first understand the basic mechanism of Hawking radiation. In the vacuum near the event horizon of a black hole, quantum fluctuations constantly give rise to pairs of virtual particles, one with positive energy, the other with negative energy. Normally, these pairs annihilate each other almost immediately. But near the event horizon, one of these particles can fall into the black hole while the other escapes. The particle that escapes becomes real and observable, while the one that falls in has negative energy relative to the outside universe. This results in a net loss of mass for the black hole, as though it is slowly bleeding energy into the void. Over unimaginably long periods, this process causes a black hole to shrink and, eventually, to vanish, leaving behind a final burst of radiation, or perhaps some quantum remnant. This slow, nearly undetectable process unfolds quietly over time, unless something catastrophic happens. Enter the black hole merger. When two black holes spiral toward each other, their space-time geometries begin to warp and interlace in ways that push both general relativity and quantum field theory to their limits. As they merge, their event horizons combine, and their singularities coalesce into a new central singularity. During this process, the gravitational landscape surrounding each black hole undergoes radical reconfiguration. Any delicate quantum mechanisms operating at or near the horizon, such as the generation of Hawking radiation, could be temporarily overridden, distorted, or even restarted altogether. One key idea is that Hawking radiation is intrinsically tied to the geometry of a black hole's event horizon. Its temperature, intensity, and particle spectrum all depend on the mass, spin, and charge of the black hole. So, when two black holes merge and form a new black hole with a different set of properties, it is natural to assume that the Hawking radiation process also changes. The new black hole might effectively reset the evaporation clock, beginning again with a new temperature and evaporation rate based on its new mass and spin. This has several implications. First, if the original black holes were evaporating slowly before the merger, that process would be effectively paused or altered as the horizons collapse and reform into a single surface. During the merger, the chaotic rearrangement of spacetime might disrupt the delicate particle-antiparticle separations that fuel Hawking radiation. In fact, in the moments immediately surrounding the merger, the environment may become too energetic and unstable to support the formation of well-defined quantum horizons. The radiation mechanism may be smothered in the case. After the merger settles and the event horizon stabilizes, a process known as the ring-down phase, the conditions may return to those necessary for Hawking radiation to begin anew. But now the black hole is larger, likely spinning, and possesses a different curvature profile. Its radiation would be cooler and less intense, since Hawking radiation decreases in temperature as the black hole's mass increases. That means that a merged black hole may actually radiate even more slowly than its parent black holes did. However, some speculative theories suggest more exotic outcomes. For instance, what if the merger is so violent that it momentarily enhances Hawking radiation? A sudden surge of negative energy particles being pulled into the forming singularity could hypothetically cause a spike in outgoing radiation, perhaps even an observable burst, though this is entirely conjectural and no such event has been observed. Some theorists propose that the intense gravitational field gradients at the merging horizons might amplify quantum effects, momentarily intensifying the rate of evaporation before things settle down. It would be like a flare of quantum heat that dies quickly as equilibrium is restored. Then there's the consideration of exotic Hawking radiation channels. In advanced models that include extra dimensions or hypothetical particles, like axions or gravitinos, mergers could open up new decay pathways. The energetic reshuffling of the vacuum could allow different particle species to be emitted temporarily. This would add complexity to the radiation signature and might create an observable deviation in the merger aftermath. If future detectors could pick up this radiation, say, in the X-ray or gamma-ray bands, it might allow us to probe these mysterious processes directly. Further complicating the picture is the role of black hole entropy and information. Hawking radiation is not just a thermal process. It plays a critical role in debates about information preservation in quantum mechanics. When two black holes merge, their entropies, proportional to their surface areas, do not simply add up. Instead, the area of the resulting black hole's event horizon is typically greater than the sum of the originals, aligning with the second law of thermodynamics. This jump in entropy might represent a reset of informational encoding on the horizon's surface. If Hawking radiation was encoding quantum information from the parent black holes, what happens to that process during the transition? Does the final black hole start fresh, or does it somehow continue the emission of a combined informational signature? This ties back into broader questions about the information paradox and the holographic principle. If all the information that falls into a black hole is encoded on its horizon, and Hawking radiation leaks that information out over time, then a merger complicates the storyline. The merger may scramble the horizon's information encoding and alter the radiation signal. In quantum gravity models, such as those involving black hole complementarity or fuzzball theory, the radiation might not restart cleanly, but instead continue to reflect the past identities of the original black holes, albeit in a jumbled fashion. There are also implications for black hole evaporation end states. If Hawking radiation is significantly disrupted or altered by a merger, it could affect whether or not a black hole ever fully evaporates. Some theories propose that evaporation halts at the Planck scale, leaving behind a tiny, stable remnant. If mergers delay evaporation by increasing mass and stabilizing the horizon, then the overall lifetime of the black hole could be extended enormously. Black holes formed by multiple mergers across cosmic time might end up being the last objects to fade from the universe. And there's the observational frontier. While Hawking radiation itself is far too faint to be observed from stellar mass or even supermassive black holes, the aftermath of mergers might create indirect signatures. Some physicists suggest that gravitational wave echoes, subtle ripples in the post-merger spacetime, could carry the fingerprints of altered quantum fields, including those associated with Hawking radiation. In the far future, more sensitive detectors could potentially catch these echoes, allowing us to test whether quantum processes like evaporation were disrupted or modified during the event. In summary, the merger of two black holes is not just an astrophysical event, it is a quantum reset of staggering proportions. Hawking radiation, that slow, gentle whisper of quantum decay, is caught in the middle of a cataclysmic fusion. Whether it pauses, intensifies, shifts, or restarts entirely remains one of the many unanswered questions on the edge of black hole physics. One thing is certain: if we ever hope to understand black holes not just as gravitational objects but as quantum entities, we must study what happens to Hawking radiation in the crucible of their most extreme transformations. Gravitational wave echoes. The universe has a way of whispering its secrets, and few whispers are more profound than the ripples in space-time known as gravitational waves. These waves, predicted by Einstein's theory of general relativity and first directly detected by LIGO in 2015, are among the most spectacular messengers of cosmic violence. When two black holes collide, they send out these space-time tremors across the cosmos, bearing the imprint of the cataclysm that birthed them. But what if these gravitational waves don't just travel as smooth, fading pulses? What if, in the aftermath of the merger, they bounce back, just faintly, just briefly, like an echo from something strange near the event horizon? This idea forms the basis of one of the most tantalizing frontiers in modern astrophysics: gravitational wave echoes. To appreciate the significance of these echoes, we must first revisit how gravitational waves behave during and after a black hole merger. When two black holes spiral into each other, they emit gravitational waves in three main phases. The first is the inspiral phase, where the black holes orbit closer and closer, their waveforms increasing in frequency and amplitude. Next comes the merger itself, a burst of raw energy where the horizons fuse and spacetime is stretched to its limits. Finally, the newly formed black hole enters the ring-down phase, during which it rings, like a struck bell, emitting gravitational waves as it settles into a stable configuration. According to classical general relativity, this ring-down produces a clean, predictable signal that rapidly fades. But some researchers argue that this isn't the end of the story. If there are exotic quantum structures just outside the event horizon, such as those predicted by certain quantum gravity models, they might partially reflect gravitational waves. The result? Faint echoes occurring milliseconds after the main merger signal, repeating at regular intervals, like the reverberation of sound in a canyon. These echoes would not only be a signature of something beyond classical physics, but they might also reveal what black holes actually are at their core. One of the major motivations behind the search for gravitational wave echoes lies in the potential breakdown of the classical event horizon. In Einstein's theory, the event horizon is a smooth, featureless boundary. Nothing can escape it, and nothing reflects off it. But several quantum theories challenge this simplicity. For example, string theory's Fuzzball concept suggests that a black hole's interior is not empty but composed of tangled strings that extend all the way to what we thought was the event horizon. In this model, there is no true horizon, just a complex surface with microstructure that can reflect or distort gravitational waves. Similarly, the Firewall hypothesis posits a high-energy barrier at the event horizon, burning anything that tries to cross. This firewall could interact with outgoing gravitational waves, creating echoes. Other models suggest that quantum fluctuations or Planck-scale remnants near the horizon could form a kind of semi-reflective membrane, subtly bouncing back energy in the form of gravitational waves. If any of these models are correct, the final signal we observe from a black hole merger wouldn't be a smooth tapering ring down. It would include tiny, repetitive echoes separated by precise intervals. The timing of these echoes depends on the distance between the horizon and the would-be reflective surface. If the structure lies just above the event horizon, a Planck length away, the echoes would arrive mere milliseconds after the main signal. Detecting such rapid reverberations would be challenging, but not impossible. In fact, some researchers believe they may have already detected them. In several studies following LIGO's detection of gravitational waves from mergers such as GW150914 and GW170817, astrophysicists have combed through the data looking for signs of echo-like patterns. Some analyses claim tentative evidence of echoes at statistically interesting levels. However, these claims remain controversial. Echoes, if they exist, are incredibly faint, often at or below the noise threshold of our current detectors. The debate continues, with some scientists urging caution and others pressing forward, convinced that we're on the verge of probing the quantum edge of black holes. The implications of confirmed gravitational wave echoes would be enormous. They would provide experimental evidence that black holes are not as simple as general relativity suggests. Echoes could reveal the structure of the surface, or pseudosurface, of the black hole, giving clues about the nature of quantum gravity and the fate of information that falls in. In essence, echoes could be the key to resolving the black hole information paradox, suggesting that black holes have more structure than we've imagined and that information might not be lost after all. There's also the possibility that echoes could help distinguish between different quantum gravity theories. For instance, loop quantum gravity predicts discrete spacetime geometries that could produce slightly different echo patterns compared to fuzzballs and string theory. If we can detect multiple echoes across various mergers, we may start to see consistent signatures, patterns in the delay, strength, or frequency profile that point toward one theoretical framework over another. But this is not just a theoretical exercise. Future gravitational wave observatories, such as the space-based LISA, Laser Interferometer Space Antenna, will be vastly more sensitive to low-frequency gravitational waves. LISA and next-generation ground-based detectors could provide the resolution needed to pick up these faint echoes with high confidence. If even one clear echo is detected with strong statistical significance, it would be a revolution in physics, equivalent to the discovery of gravitational waves themselves. Moreover, echoes could teach us about phenomena we never expected. They might show variability based on the spin or mass of the merging black holes. Or they might interact with exotic fields or dark matter surrounding the black holes, producing subtle modulations that enrich our understanding of both black hole physics and cosmology. They could even reveal entirely new particle interactions that don't manifest elsewhere in nature. Of course, some skeptics argue that what we're interpreting as echoes might just be noise or artifacts in the data processing. Indeed, the statistical significance of many claimed echoes is still under debate, and no detection has yet reached the 5 sigma gold standard in physics. But science often begins in whispers, faint signals that challenge our assumptions. The story of gravitational wave echoes, whether it leads to confirmation or refutation, will push our detectors, our theories, and our imagination to the limits. Echoes are more than just a search for new physics, they are a question about reality itself. Is the event horizon truly a perfect, one-way membrane, or is it a shimmering, quantum-structured veil, rich with microstates and surprises? Are black holes the ultimate simplifiers of the universe, or are they windows into deeper layers of complexity? Gravitational wave echoes offer a rare chance to listen, closely, carefully, to the aftershocks of creation and destruction at the heart of space-time. If we keep listening, perhaps the universe will speak. Planck-scale remnants? When two black holes collide and merge into a larger one, classical general relativity tells us that all we're left with is a final black hole described by just a few parameters: mass, spin, and charge. But this classical view starts to unravel when we peer closely, microscopically, at the moment of merger. At the very core of each black hole lies a singularity, a point of infinite density where the known laws of physics cease to function. It is here, deep inside, that some theorists believe something astonishing may occur: the formation, or perhaps the survival, of a Planck-scale remnant, a tiny but fundamentally important structure with implications for the fabric of reality itself. The Planck scale represents a threshold far beyond the reach of current particle accelerators. It's the realm where gravity becomes as strong as the other fundamental forces and quantum effects can no longer be ignored. At the Planck length, about 1.6 times 10 superscript 3 meters, and Planck mass, approximately 2.2 times 10 kilograms, we enter a zone where classical descriptions break down completely. Many physicists believe this is where a true theory of quantum gravity must emerge, uniting general relativity and quantum mechanics into a coherent whole. Now consider a black hole merger from this perspective. When two singularities plunge together, all their mass energy and all their information theoretically compress even further. But if there's a fundamental limit to how small or dense something can become, a limit imposed by quantum gravity, then the merger might not yield a smooth, featureless black hole interior. Instead, at the heart of this monstrous object, a tiny Planck-scale remnant may remain. This core would be beyond our current observational reach, but its existence could solve several long-standing problems in physics. One of those problems is the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. Yet black holes, if they evaporate through Hawking radiation as predicted, appear to erase the information about everything that fell into them. But what if, when all the mass of a black hole evaporates, a small remnant remains, a stable object the size of the Planck scale, still containing the compressed information of the black hole's entire history? This remnant would act as a kind of quantum vault, never evaporating fully, preserving the integrity of quantum information. Such remnants may also serve as candidates for dark matter. One of the great mysteries in cosmology is the unseen mass that holds galaxies together and influences the structure of the universe. Planck-scale remnants, if they were produced in large quantities in the early universe, or if they accumulate through black hole mergers, could represent a form of non-luminous, non-interacting matter with gravitational effects. Though they'd be nearly impossible to detect directly, their presence could have left imprints on the cosmic microwave background or on gravitational wave signals. Of course, the very idea of a Planck-scale remnant is speculative and controversial. For one, it challenges the concept of complete black hole evaporation. Hawking radiation predicts that black holes gradually lose mass and shrink, becoming hotter and more intense in radiation until they vanish entirely. But if a remnant persists, this implies a mechanism that halts evaporation at a certain point. Theoretical models like the Generalized Uncertainty Principle, GUP, suggest exactly that, a modification of Heisenberg's uncertainty principle that becomes important at the Planck scale, preventing total collapse and leading to the stabilization of a minimal structure. Some versions of loop quantum gravity offer further support. In these models, space itself is quantized, composed of tiny, discrete loops. When applied to black hole interiors, loop quantum gravity sometimes replaces the classical singularity with a finite dense core, effectively a Planck-scale region where the collapsing matter bounces, instead of reaching infinite density. This bounce may even lead to phenomena like baby universe creation, but at its heart lies a remnant, a compressed nugget of quantum spacetime that resists further collapse. Planck-scale remnants might also explain black hole complementarity, the idea that from the outside, nothing seems to survive a plunge into a black hole, but from a different perspective, such as an infalling observer, information might still persist in a different form. The remnant acts as a sort of compromise. To an external observer, the black hole seems to evaporate, but something is still there, locked inside the Planck-scale vault. Interestingly, these remnants could have properties that defy normal expectations. They might carry exotic charges, strange topologies, or even degrees of freedom we haven't discovered yet. They might be unobservable in conventional ways, or they might interact only via gravity, rendering them effectively invisible to all standard model particles and forces. In some quantum gravity proposals, the remnant's entropy scales not with its mass but with its information content, allowing it to store a staggering amount of quantum data in an unfathomably small volume. Could we ever detect a Planck-scale remnant? Directly, it seems unlikely with current technology. These objects would be smaller than anything we can probe, and their gravitational influence would be minuscule unless present in vast numbers. However, indirect detection might be possible. For example, if black hole mergers occasionally produce or eject remnants, we might see small discrepancies in gravitational wave signals, tiny missing mass that doesn't show up in the final black hole. Or we might notice unexplained energy thresholds in cosmic ray spectra or subtle variations in Hawking radiation if quantum remnants interfere with the evaporation process. There's also the provocative question of stability. If remnants are truly stable, could they accumulate over cosmic time, forming clusters or halos around galaxies? Could they form new types of compact objects or serve as seeds for future black holes? Or might they be inherently unstable, decaying into other exotic particles over unimaginably long timescales? From a philosophical perspective, Planck-scale remnants raise fundamental questions about the nature of reality. If everything that has ever fallen into a black hole still exists in some compressed, preserved state, then nothing is ever truly lost. Every photon, every atom, every consciousness that crossed an event horizon still echoes through the universe, reduced to something unimaginably small but eternally persistent. In this way, remnants challenge our understanding of death, loss, and the finality of cosmic processes. As we continue to probe deeper into the behavior of black holes through gravitational wave astronomy, quantum field theory, and theoretical models of spacetime, the possibility of Planck-scale remnants remains one of the most intriguing. It's a convergence point for quantum mechanics, relativity, information theory, and cosmology, a place where our current theories falter, but where something new, perhaps revolutionary, may begin. Loop quantum gravity effects. As we descend deeper into the heart of black hole collisions, beyond the smooth fabric of spacetime envisioned by Einstein's general relativity, we reach the strange, granular terrain proposed by one of the most ambitious theories of quantum gravity, loop quantum gravity, LQG. Unlike string theory, which seeks to explain particles as vibrating strings within multidimensional space, loop quantum gravity focuses directly on the fabric of spacetime itself, asserting that space and time are not continuous, but made up of tiny, indivisible building blocks, much like atoms are for matter. In the context of black hole mergers, this discretization of space has enormous implications. Classical general relativity paints spacetime as a smooth, infinitely divisible field that curves in response to mass and energy. However, when two black holes collide, they generate gravitational fields of such immense intensity that the assumptions of smoothness begin to break down. Loop quantum gravity steps in here, suggesting that at scales close to the Planck length, spacetime is quantized into loops, or spin networks, forming a kind of quantum scaffolding. This changes everything we thought we knew about how space and time behave under extreme conditions. At the core of every black hole lies a singularity in classical physics, a point of infinite density and zero volume. But LQG challenges this notion. According to loop quantum gravity, singularities don't actually exist in the traditional sense. Instead of collapsing into a point of infinite curvature, matter and energy compress only until they reach a fundamental minimum size, at which point quantum gravitational repulsion counters further collapse. This concept, often described as a quantum bounce, could be dramatically revealed during a black hole merger. When two black holes collide and their singularities converge, rather than forming an even deeper gravitational abyss, loop quantum gravity suggests that the spacetime in their cores resists further collapse, forming a highly compressed region governed by discrete geometry. The merger doesn't end in a catastrophic singularity but rather in a new, extremely dense state of matter and geometry, still hidden behind the event horizon but now potentially governed by different laws than previously assumed. The implications of this are profound. First, it addresses the singularity problem of general relativity by replacing infinities with finite quantum structures. Second, it opens the door to non-singular black hole models, where the interior of the merged black hole may possess a quantum core governed by loop dynamics, a core that might someday be accessible through indirect observations or theoretical modeling. One of the most fascinating ideas arising from LQG is that during a black hole merger, the violent tearing and warping of spacetime could temporarily expose or disturb this discrete structure. While we can't observe these quantum structures directly, the gravitational waves produced during the merger might carry subtle imprints, tiny deviations from the smooth waveforms predicted by classical general relativity. These imprints are known as quantum gravitational signatures. Such signatures could appear as unexpected echoes, phase shifts, or damping effects in the post-merger gravitational wave signal, the so-called ring-down. If future detectors with even greater sensitivity, like the Einstein telescope or cosmic explorer, were to find these anomalies, it would be a groundbreaking hint that spacetime isn't smooth after all, but made of something fundamentally granular. There's also the question of how information behaves in such a quantum geometric landscape. In traditional black hole models, information appears to vanish into the singularity, creating the infamous black hole information paradox. But in loop quantum gravity, because the singularity is replaced by a finite, discrete core, there is a theoretical avenue for information to be preserved in the quantum states of the spin network that constitutes the core. If this is true, then during or after a merger, information might not be lost, but instead encoded in the quantum geometry of the resulting black hole. Interestingly, loop quantum gravity also has implications for cosmic censorship. This principle asserts that singularities must always be hidden behind event horizons. But if singularities are replaced with quantum structures that don't behave classically, does cosmic censorship still apply? Could there be conditions under which these quantum regions become visible, even fleetingly, during a collision? This remains an open question, but it lies at the intersection of quantum gravity, astrophysics, and observational cosmology. Another prediction of loop quantum gravity that might manifest in mergers is the idea of discrete spectra for geometrical quantities. In classical physics, the area or volume of a region of space can be any value. But in LQG, these quantities come in discrete packets, quantized just like the energy levels of electrons in an atom. During a merger, the changing geometry of spacetime could transition through a sequence of these discrete states, akin to quantum jumps. While this might not be observable directly, it could subtly alter the gravitational waveform or the timing of the ring down, offering clues to this hidden discreteness. Moreover, some LQG-inspired models suggest that black hole interiors are not only non-singular but may also contain a sort of bridge to another region of spacetime, a white hole, or even a separate universe entirely. If so, the merger of two such black holes could create a complex quantum geometric object that momentarily connects regions of space and time in ways we can't yet fully comprehend. As the field progresses, physicists are developing effective models that bridge classical and quantum descriptions, allowing them to simulate black hole mergers in frameworks that incorporate loop quantum gravity effects. These models aim to predict specific observables, like gravitational wave anomalies, energy spectrum alterations, or deviations in black hole thermodynamics, that could one day validate the theory. The beauty of loop quantum gravity in the context of black hole collisions lies in its ability to unify the microscopic and macroscopic. It posits that even in the most violent, large-scale events in the cosmos, the fundamental rules are governed not by smooth continua but by an underlying lattice of quantum threads. Black hole mergers may be our only natural laboratories for exploring this exotic realm. In a sense, these events become like cosmic particle accelerators, compressing space-time and energy into conditions where the loop structure might emerge, not as speculation, but as reality. If we can read these gravitational wave signals correctly, decoding the whispers of space-time itself, we might finally glimpse the quantum nature of the universe. Fuzzball theory. As we venture into the realm of string theory to understand black hole mergers, we encounter one of the most radical reimaginings of what a black hole actually is, the fuzzball theory. Traditional physics treats black holes as having a central singularity, an infinitely dense point where the laws of physics break down, surrounded by an event horizon from which nothing escapes. However, fuzzball theory, a concept born from string theory, proposes a dramatically different picture that challenges this classical view at its core. According to fuzzball theory, the concept of a singularity is replaced by a fuzzball, a complex, tangled mass of fundamental strings and branes, the tiny one-dimensional objects string theory posits as the building blocks of all particles and forces. Instead of being a smooth point of infinite density, the black hole interior is a chaotic, high-dimensional quantum object, stretching across the region that general relativity would classify as the event horizon and interior singularity. What does this mean for black hole mergers? When two black holes collide, under fuzzball theory, what actually merges are these enormously complicated, intertwined configurations of strings. Instead of two point-like singularities combining, it is two vast, extended quantum structures, each composed of an astronomical number of microstates, that swirl together and interact. These microstates represent the different possible arrangements of strings and branes that account for the black hole's entropy, providing a microscopic explanation for the enormous information content hidden within black holes, a major unresolved problem in classical black hole physics. The fuzzball proposal is particularly appealing because it offers a resolution to the infamous black hole information paradox. In classical theory, information about matter falling into a black hole seems lost forever, violating the laws of quantum mechanics which require information conservation. In the fuzzball picture, the complex string configurations that make up the fuzzball encode information in their microstates, meaning that information is not destroyed but stored in the quantum structure of the fuzzball itself. During a merger, the fuzzballs would interact through their extensive networks of strings, exchanging and rearranging these microstates in ways far more complicated than the merging of classical singularities. This process would produce gravitational waves, but potentially with subtle signatures revealing the quantum structure of spacetime itself. The detailed dynamics of this interaction remain an active area of research, as theorists attempt to reconcile the mathematics of string theory with observable astrophysical phenomena. One intriguing aspect of fuzzball mergers is how the event horizons behave. In classical general relativity, the event horizon is a smooth, well-defined surface surrounding the singularity. But fuzzballs suggest the horizon is not a sharp boundary but a fuzzy surface, full of quantum structure and fluctuations. When two fuzzballs collide, their horizons would merge in a complex quantum dance, potentially producing novel gravitational wave signatures different from classical predictions. These deviations could be tiny but detectable with future generations of gravitational wave observatories. Moreover, because fuzzballs are extended objects, their merger dynamics could involve stringy phenomena such as string oscillations, reconnections, and the excitation of higher-dimensional branes. These quantum interactions could release exotic particles or radiation during or after the merger, contributing to phenomena not predicted by classical models. Some speculate this could even relate to the mysterious signals sometimes observed in high-energy astrophysics, although this remains speculative. Fuzzball theory also provides a fascinating perspective on the structure of the interior of the merged black hole. Instead of a classical singularity where density and curvature diverge infinitely, the merged fuzzball is a vast, tangled ball of strings whose size corresponds to the classical black hole radius. This means there is no singular point hidden inside, just a highly excited quantum state, made up of countless strings vibrating in complex patterns. The merger thus results in a combined fuzzball whose microstate complexity is vastly greater than that of either original black hole. This has implications for the final spin, charge, and mass of the new black hole. Unlike the classical picture where these parameters simply add, the fuzzball merger would be influenced by the detailed quantum state of the strings, potentially producing outcomes that deviate subtly from classical expectations. For example, some of the merger energy might go into exciting string modes, rather than only into gravitational waves or black hole mass increase. Because fuzzball theory arises from string theory's higher dimensional framework, it also ties into ideas about extra dimensions. The strings composing fuzzballs can wrap and vibrate in multiple spatial dimensions beyond the familiar three, meaning that black hole mergers could involve interactions not only in our observable universe but also in hidden dimensions. This could influence the dynamics of mergers and the resulting gravitational wave patterns. In the broader cosmic context, fuzzball mergers might offer clues about the ultimate unification of forces and particles. Since the fundamental strings of fuzzballs are the same strings that string theory proposes make up all matter and forces, studying these mergers could provide rare glimpses into the deepest layers of reality where gravity, quantum mechanics, and particle physics converge. Observationally, detecting signatures of fuzzball mergers is extremely challenging. Current gravitational wave observatories like LIGO and Virgo measure signals consistent with classical black hole mergers, but the precision needed to tease out quantum string effects is beyond current capabilities. Future detectors, especially space-based observatories such as LISA, Laser Interferometer Space Antenna, with their sensitivity to lower frequency waves and longer duration signals, might offer a window into these subtle quantum effects. Moreover, advances in theoretical physics, computational modeling, and numerical relativity will be essential for making precise predictions about how fuzzball mergers differ from classical mergers, enabling us to know exactly what to look for in gravitational wave data. Fuzzball theory reshapes the black hole merger narrative by replacing the singularity with a quantum tangle of strings. Instead of a simple union of point-like gravitational wells, merging black holes are colliding clouds of quantum strings, each with immense complexity and information content. The interaction of these fuzzballs during a collision is a rich, dynamic quantum event with potential observational consequences that might one day unlock new chapters in our understanding of gravity, quantum mechanics, and the fundamental nature of the universe. Holographic principal impact. One of the most profound and intriguing ideas born from theoretical physics in recent decades is the holographic principle. It offers a revolutionary way of thinking about space, information, and gravity, especially when it comes to black holes and their mysterious interiors. When black holes collide and merge, this principle gains a particularly fascinating significance, reshaping how we conceive of the fate of information and the structure of the resulting black hole. The holographic principle, first proposed by physicists Gerard T. Hooft and Leonard Susskind in the 1990s, is inspired by the behavior of black hole entropy discovered by Jacob Bekenstein and Stephen Hawking. They found that the entropy, a measure of information content or disorder, of a black hole is proportional not to its volume, but to the area of its event horizon, the two-dimensional surface surrounding it. This suggested that all the information about what falls into the black hole, which presumably disappears behind the horizon, is actually encoded on this horizon surface, much like a hologram encodes three-dimensional information in a two-dimensional surface. This principle proposes a radical reduction in dimensionality. A volume of space with gravity can be fully described by data encoded on its boundary. In other words, the 3D world inside the black hole might be fully projected from a 2D surface at the event horizon. This idea has deep implications for quantum gravity, string theory, and the long-standing black hole information paradox. The puzzle of how information about matter that falls into a black hole might be preserved rather than lost forever. Now, when two black holes collide, the holographic principle implies that the information originally encoded on each black hole's event horizon doesn't vanish. Instead, the information from both black holes merges and becomes encoded on the new, larger event horizon that forms after the merger. The surface area of this new horizon corresponds to the combined entropy of the system, reflecting the enormous amount of information hidden within the merged black hole. The process of this information merging and encoding onto the final event horizon is extraordinarily complex and quantum mechanical in nature. Each initial black hole's horizon encodes a vast array of quantum microstates, unique configurations of quantum information representing all the matter, radiation, and quantum fields that formed or fell into it. When these horizons combine, their quantum information microstates must also combine in a consistent way that respects the laws of quantum mechanics and gravity. This encoding process is not simply an additive operation. The holographic principle suggests that the combined horizon is a new quantum system with microstates that are more than just the sum of the parts. The quantum correlations, entanglement, and information content become intertwined, producing a richer, more intricate holographic code. This complexity might hold the key to understanding how information is preserved during black hole mergers, avoiding total information loss, and thus providing a pathway to resolving the information paradox. In fact, this principle extends beyond black holes to the universe itself. The holographic idea has been generalized into the ADS/CFT correspondence, a duality discovered by Juan Maldacena, which connects gravity in a higher dimensional curved space, anti-de Sitter space, to a quantum field theory without gravity living on the lower dimensional boundary. While our universe does not exactly correspond to this geometry, the holographic principle inspires the notion that spacetime and gravity might be emergent phenomena arising from more fundamental quantum informational processes on lower dimensional boundaries. Returning to the black hole merger, this holographic view means that the event horizon's surface is not a passive boundary but an active quantum membrane, encoding all the history and information of the black holes that formed it. The merger causes this quantum membrane to dynamically reconfigure, blending information from two black holes into a new holographic code. This has intriguing consequences for gravitational wave signals, as the quantum structure of the horizon might subtly affect the waves emitted during and after the merger. Some physicists speculate that detailed study of gravitational waveforms could reveal hints of this holographic information processing, though current detectors lack the sensitivity to observe such effects. Moreover, the holographic principle supports the idea that black hole entropy and information capacity are finite and proportional to horizon area, implying a fundamental limit to the amount of information a black hole can store. After a merger, the increase in horizon area, observed as a larger event horizon, reflects a new entropy and a new holographic encoding that encompasses the combined histories of the initial black holes. One fascinating implication is the relationship between this encoded information and Hawking radiation, the slow evaporation process theorized by Stephen Hawking, where black holes lose mass by emitting particles. The holographic principle implies that information about the interior black hole states could be encoded on the horizon and eventually radiated away through Hawking radiation, preserving unitarity in quantum mechanics and preventing information loss. Current research in quantum gravity and string theory continues to explore how exactly this holographic encoding works during dynamic events like mergers. Scientists are developing models that attempt to explicitly describe the quantum microstates on the horizon and how these evolve as black holes collide and settle into a final stable state. In summary, the holographic principle's impact on black hole mergers represents a profound shift in understanding. Instead of information being lost inside a black hole's interior, it is preserved and intricately encoded on the surface of the event horizon. When two black holes collide, their vast stores of information do not vanish but combine into a new holographic code written on the final event horizon's surface. This quantum encoding not only conserves information but could provide the key to unifying gravity and quantum mechanics, helping to unravel one of physics' greatest mysteries: quantum tunneling post-merger. When we think of black holes, we usually imagine a place of no return, where everything, matter, light, and information, gets trapped forever behind the event horizon. However, modern physics suggests the picture is far more subtle and fascinating, especially when quantum effects come into play. One such intriguing concept is quantum tunneling post-merger, the possibility that quantum mechanical processes could allow particles or even information to escape from the merged black hole, challenging classical notions of absolute entrapment. Quantum tunneling is a well-understood phenomenon in quantum mechanics. It allows particles to pass through energy barriers that classical physics deems impossible. This counterintuitive behavior arises because particles behave like waves with probabilistic distributions rather than point-like objects with fixed trajectories. Even when faced with a barrier higher than their classical energy, quantum particles have a finite probability to tunnel through and appear on the other side. This phenomenon underpins many modern technologies, such as semiconductors and nuclear fusion in stars. Applying this concept to black holes, especially after they merge, opens the door to revolutionary ideas. Classically, the event horizon acts as a perfect boundary. Nothing can cross from inside to outside. But quantum mechanics suggests the horizon is a more complex, fluctuating boundary where quantum effects might blur this rigid divide. The intense gravitational environment near the horizon, combined with quantum uncertainty, raises the possibility that particles, or perhaps even information encoded in quantum fields, could tunnel through this barrier. After two black holes collide and merge into a larger black hole, the event horizon reshapes and stabilizes. But during and after this violent merger, the horizon's quantum structure could become highly dynamic and fuzzy. This dynamism might increase the probability of quantum tunneling events at or near the horizon. Instead of an impermeable wall, the event horizon may behave like a semi-permeable quantum membrane, occasionally allowing tiny amounts of information or particles to leak out, not unlike Hawking radiation, but potentially involving more direct quantum tunneling. One key reason this idea is compelling relates to the black hole information paradox. The puzzle of how information about the original matter and radiation that formed or entered the black hole can be preserved in a universe where classical black holes erase all traces. Quantum tunneling post-merger offers a mechanism by which information could escape the merged black hole without violating the fundamental principles of quantum mechanics, including unitarity, which states information cannot be destroyed. This tunneling might involve not just individual particles, but quantum states or correlations that carry information. Quantum entanglement could allow encoded information inside the black hole to affect particles tunneling outward, effectively transmitting information back into the observable universe. In this view, the event horizon acts less like a hard boundary and more like a quantum firewall or veil, with semi-transparent qualities on a microscopic scale. The idea of quantum tunneling also intersects with theories that propose quantum gravity corrections to classical black hole physics. Quantum gravity attempts to unify general relativity, which governs large-scale gravity, with quantum mechanics, which governs small-scale particle behavior. Several models suggest that near the Planck scale, the smallest meaningful scale in physics, the structure of spacetime and horizons becomes discrete and probabilistic, enhancing the possibilities for tunneling-like phenomena. Moreover, quantum tunneling post-merger could influence observable astrophysical phenomena. For example, it might subtly affect the spectrum and timing of Hawking radiation, potentially increasing the rate or altering the character of emitted particles. It could also generate tiny bursts or fluctuations in radiation escaping the vicinity of the black hole, which future ultrasensitive detectors might detect as anomalous signals. In the context of gravitational waves, the ripples in spacetime produced by black hole mergers, quantum tunneling might introduce subtle quantum signatures or noise in the waveforms. Although current gravitational wave observatories like LIGO and Virgo detect primarily classical signals, next-generation detectors could look for tiny deviations that hint at quantum mechanical processes near horizons, including tunneling-induced phenomena. Another fascinating aspect concerns the fate of quantum information entangled with the black hole's interior. If particles or quantum bits, qubits, can tunnel out post-merger, then the final black hole might slowly release the accumulated information from the two progenitor black holes, not instantaneously but gradually over vast timescales. This scenario paints a more nuanced picture of black hole evaporation and information recovery, potentially solving long-standing theoretical puzzles. Quantum tunneling post-merger also aligns with speculative ideas about black hole complementarity and the Firewall paradox. Black hole complementarity suggests that information is both reflected at the horizon and passes through it without contradiction, depending on the observer's viewpoint. Quantum tunneling could be a physical mechanism underlying this dual perspective, facilitating the escape of information in a way compatible with both perspectives. Conversely, the Firewall hypothesis proposes a high-energy zone near the horizon that destroys information. Tunneling offers an alternative, less destructive route for information release. Despite its theoretical appeal, quantum tunneling post-merger remains deeply speculative and challenging to test experimentally. It requires merging the mathematical frameworks of quantum field theory, general relativity, and potentially unknown quantum gravity theories. However, ongoing advances in gravitational wave astronomy, black hole simulations, and quantum information theory continue to refine our understanding and may one day reveal observational evidence supporting or refuting this idea. Quantum tunneling post-merger challenges the classical notion of black holes as perfect prisons. By introducing quantum mechanical leakage, it offers a possible pathway for particles and information to escape even after the dramatic collision of two black holes. This process may not only illuminate the resolution of the black hole information paradox but also deepen our understanding of the quantum fabric of spacetime, horizons, and the ultimate fate of black holes in our universe. Violation of locality. In classical physics and even most of quantum mechanics, the principle of locality reigns supreme. Locality is the idea that objects are only directly influenced by their immediate surroundings. In other words, cause and effect happen in close proximity. If you push a ball, it rolls because your hand touched it, not because something miles away affected it instantly. This assumption is baked into nearly every model of physics we use. But what if this fundamental rule breaks down in the most extreme corners of the universe, such as during the collision of two black holes? This is not just a philosophical musing. In theoretical physics, especially in studies involving quantum gravity and black holes, there's growing suspicion that locality might not be fundamental. Instead, it may be an emergent property that only holds true at large scales, but dissolves in the intense, ultra-compressed environments where space and time themselves stretch and warp beyond recognition. The idea of violation of locality suggests that during a black hole collision, when mass, energy, and curvature of spacetime reach unfathomable levels, the traditional framework of cause and effect may disintegrate. Events at one point in spacetime could become instantly correlated with events at vast distances, not due to any signal traveling faster than light, but because the concept of distance might lose meaning altogether at that scale. This proposition is not baseless speculation. It emerges from ongoing work in quantum field theory, string theory, loop quantum gravity, and especially holographic dualities like the ADS/CFT correspondence. These theoretical tools suggest that in some models of quantum gravity, Space-time itself is not fundamental. Instead, it arises from more basic quantum informational processes. If space-time is emergent, so too is locality, and therefore, it can break down under the right conditions. Black hole mergers may be one such condition. When two black holes spiral together and collide, the geometry of spacetime becomes extraordinarily complex. Their event horizons warp and twist, and at the center, their singularities, regions where classical descriptions of space and time fail, are merging. If spacetime is composed of discrete, entangled units, as proposed in loop quantum gravity, these units may no longer adhere to the spatial relationships we're familiar with. In a very real sense here, and there, may cease to be distinguishable. This has radical implications. In such a non-local merger, changes or interactions occurring near one horizon could immediately influence events at the other, even if they were separated by vast spatial distances before merging. These correlations might not require any signal to travel through space at all. They're baked into the quantum structure of the system itself. This would mean that information, energy, and influence could be redistributed throughout the merged black hole almost instantaneously, governed by quantum connectivity rather than classical geometry. Theoretical support for non-locality also comes from black hole entanglement models. In these models, particles and fields that fall into a black hole become deeply entangled with the internal quantum states of the black hole itself. But because of this entanglement, changes in one part of the system can correlate with others, no matter the spatial separation. This form of quantum connectedness isn't a loophole or trick, it's a foundational aspect of quantum reality. During a black hole collision, when vast amounts of matter and energy become interwoven in quantum chaos, the entire internal system could become a web of non-local interactions. There's also another theoretical trigger for locality breakdown, the holographic principle, which asserts that all the information contained within a volume of space can be described by data on the surface enclosing it. This principle, when applied to black holes, means the 3D reality we perceive inside the black hole might actually be encoded in a 2D surface at the horizon. In such a scenario, traditional ideas of location inside the black hole collapse. Locality inside the volume is simply a projection, it has no real basis. Therefore, as two black holes merge and their event horizons combine, the surface encoding this information changes, leading to a complete redistribution of quantum information that ignores classical distance constraints. This violation of locality may also connect with ER equals EPR, a controversial but influential conjecture proposed by physicists Leonard Susskind and Juan Meldacena. It posits that Einstein-Rosen bridges, wormholes, are equivalent to entangled particles, EPR pairs. If this conjecture holds, then the merged black hole might contain a maze of microscopic wormholes connecting all internal quantum states. These wormholes would allow for instant correlations across any distance inside the black hole, effectively nullifying locality. And there's more. If such non-local behavior is real, it could have tangible consequences outside the black hole as well. For instance, gravitational wave signals might carry subtle imprints of non-local interactions, leading to phase shifts, irregular harmonics, or quantum echoes that defy classical prediction. Although current detectors like LIGO and Virgo aren't sensitive enough to identify such faint signatures, future instruments such as LISA or Cosmic Explorer might have the resolution to detect them. Another angle worth considering is the role of non-locality in solving the information paradox. If information inside a black hole is not confined to a specific region but instead exists in a globally entangled state, then it might be retrievable via external correlations, perhaps through Hawking radiation or post-merger quantum emissions. This possibility would be a profound victory for physics, preserving the sacred laws of quantum mechanics while rewriting our understanding of space and time. Still, the idea of locality breaking down is deeply unsettling to many physicists. It challenges centuries of intuition and mathematical frameworks built on the assumption of nearby cause and effect. It suggests that space and time, the very stage upon which all physics unfolds, might be illusions, emergent properties of deeper, hidden processes not confined by classical constraints. Yet black hole collisions, the most extreme events in the known universe, may be the very place where this hidden reality briefly peeks through. In the throes of merging horizons, collapsing singularities, and quantum chaos, the universe may temporarily shed its mask of locality and reveal a tapestry of instant connectivity, global interactions, and non-spatial relationships that transcend our deepest intuitions. Collapse into a Planck star. Among the most compelling ideas to emerge from attempts to unite general relativity and quantum mechanics is the notion of the Planck star, a hypothetical, ultra-dense object that may represent the true endpoint of gravitational collapse. The concept is not just a reimagining of a singularity, but a total reframing of what happens at the very heart of black holes. In classical general relativity, when two black holes merge, their singularities coalesce into a new, larger singularity, a point of infinite density and zero volume. But infinities make physicists nervous. They're often taken as a sign that our understanding breaks down at that scale. So, what if, instead of a singularity, a Planck-scale quantum object forms at the core of the merged black hole? The Planck star hypothesis originates from research in loop quantum gravity, LQG, a leading candidate for a theory of quantum gravity. In LQG, space-time itself is not smooth and continuous, but instead composed of tiny, discrete loops woven together into a quantum fabric. At extremely small scales, on the order of the Planck length, about 1.6 times 10 to the power of negative 35 meters, space and time cease to behave classically. This provides a natural cutoff to the infinite density problem. Rather than allowing the gravitational collapse to continue indefinitely into a singularity, quantum pressure counteracts gravity when a certain density threshold is reached, halting the collapse and rebounding it. This is the key idea behind the Planck star. Imagine two black holes spiraling into one another, distorting spacetime, generating gravitational waves, and finally merging in a colossal explosion of energy. At the heart of this collision, their singularities would not form a new infinite point, but rather compress into a Planck-sized core, a region where quantum gravitational effects dominate, and where a bounce may occur. This rebound doesn't happen in normal time, though. Due to the extreme warping of spacetime within the event horizon, what might be a rapid event inside the black hole could appear to take billions of years from the outside. In essence, the Planck star may be a quantum object that looks like a black hole for an extremely long time but is actually a temporary state, possibly even a gateway to something beyond. If such Planck stars exist, their formation would dramatically alter what we think we know about black hole mergers. The final object left behind wouldn't be a true black hole with an infinitely dense singularity, but a finite, though staggeringly dense, remnant, potentially stable, or potentially subject to a delayed quantum decay. This has massive implications. It suggests that information trapped inside black holes might eventually be released, sidestepping the black hole information paradox. Instead of being lost forever, the information encoded in all the matter and radiation that fell into the original black holes could, in theory, re-emerge, perhaps billions of years later, when the Planck star either explodes or leaks its contents via quantum processes. There's also the tantalizing possibility that Planck stars are observable. While still highly speculative, some models predict that their explosive re-expansion could release intense bursts of high-energy particles or radiation. If this process occurred in a time-dilated frame, where billions of years pass externally while only moments elapse internally, it might match the timescales of observed phenomena like fast radio bursts, FRBs, or gamma-ray bursts, GRBs. While these events are currently attributed to other astrophysical mechanisms, the possibility that some may originate from decaying Planck stars has not been completely ruled out. During a black hole merger, the combined mass and energy reach such extreme levels that they may trigger quantum gravitational effects earlier than expected. Instead of forming a singularity that waits until the black hole's hypothetical end via Hawking radiation trillions of years in the future, the merged core might already be at the Planck threshold. In this view, the collision doesn't deepen the singularity, it replaces it. The merger becomes not an eternal death knell of mass into a void, but a quantum furnace whose destiny might be more cyclical than terminal. From a theoretical standpoint, Planck stars could also bridge several disparate ideas in modern physics. They offer a path to reconcile black hole entropy with unitary quantum mechanics. They may align with bounce cosmology models, in which our universe itself was born not from a singularity, but from the rebounding of a Planck-scale core in a previous universe. They also complement ideas like the holographic principle, suggesting that the final event horizon might not only encode information, but act as a dynamic membrane that gradually reveals quantum processes from within. In the context of mergers, there's also an open question of how gravitational waves would behave. If the interior object is a Planck star rather than a classical singularity, would the ring-down phase differ? Would the frequencies shift subtly due to a different core structure? Could gravitational wave detectors one day resolve these differences, enabling us to distinguish between a true classical black hole and a Planck star core? It's unknown, but future detectors with greater precision might begin to probe these ultra-subtle features. Then there's the question of stability. If a Planck star is not infinitely dense, is it immune to collapse under further accretion? Can it grow? Does it have a maximum mass before transitioning into something else entirely, maybe even an exotic object beyond current theory? Some theorists suggest that repeated mergers involving Planck stars might accumulate quantum stress, eventually triggering a phase transition. The outcome? Anything from a sudden quantum explosion, to the formation of an entirely new spacetime region, or the birth of a new universe, connecting us back to previous speculative ideas like baby universes or multiverse gateways. Though experimental validation is still far off, the Planck star concept remains one of the most promising candidates for resolving the black hole singularity issue. It combines the best of quantum gravity's insights with the violent, dramatic astrophysics of black hole mergers, opening the door to possibilities far stranger, and more hopeful, than a universe of infinite dead ends. Annihilation via anti-black holes. This idea begins with a daring question: what if black holes, like particles, can come in both matter and antimatter varieties? While black holes themselves are regions of spacetime and not particles per se, they are formed from collapsed matter. So if there were regions in the early universe where antimatter dominated, it stands to reason that antimatter black holes, formed from collapsing antimatter stars or clouds, might exist. And if such objects still roam the cosmos, a merger between a regular black hole and an antimatter black hole could be unlike anything else in the universe, a cosmic-scale annihilation. On a particle level, when matter and antimatter meet, they annihilate in a burst of pure energy. An electron meeting a positron results in the release of high-energy photons, gamma rays. Theoretically, a proton meeting an antiproton leads to a similar conversion into radiation. The energy released per particle pair is enormous on a microscopic scale. But now imagine entire black holes, whose masses can be several times that of the Sun, composed of these fundamental antimatter particles. So what happens when these titanic opposites collide? At first glance, one might assume that such a collision would cause the immediate annihilation of both black holes into a universe-shaking gamma-ray burst. But the reality is likely more nuanced and fascinating. Because black holes are defined by their mass, spin, and charge, not by the type of matter they formed from, there may be no externally measurable distinction between a matter black hole and an antimatter one. In classical general relativity, the no-hair theorem asserts that black holes have no hair, meaning they retain no other information about the nature of the material that collapsed to form them. If that's the case, then black holes formed from antimatter should be indistinguishable from those formed from matter, at least from the outside. But let's entertain a deeper possibility, that black holes do, in some way, preserve the quantum signature of the particles they were made from. If this is true, then when a matter black hole and an antimatter black hole merge, the event could be governed by quantum mechanical principles, rather than purely classical ones. As the two horizons approach, the tidal distortions and the immense spacetime curvature could bring the outer layers of their quantum structures into contact first. This would initiate annihilation not at the level of classical geometry, but at the quantum boundary layer, the skin, of the black hole, so to speak. This quantum-scale annihilation, multiplied across trillions upon trillions of particle-antiparticle interactions, could release an absolutely staggering amount of energy. It would not be like normal black hole mergers that primarily emit gravitational waves. This event might unleash a blinding flood of high-frequency gamma rays, neutrinos, and perhaps exotic particles. If a portion of the mass is converted to energy during this process, the merger might result in a final black hole significantly smaller than the sum of its parts, in contrast to typical mergers where most of the mass is conserved minus the gravitational radiation. The missing mass would instead go into radiation, possibly producing signals that look completely different from standard black hole mergers, signals that would stand out in LIGO, Virgo, or future high-energy observatories. A mismatch in the energy balance could be a crucial clue, potentially hinting that something far more exotic had occurred. Another speculative avenue arises when we ask, could the annihilation of matter and antimatter black holes destroy the event horizon itself? If enough energy were liberated in a localized zone on or near the horizon, it might generate a quantum disruption of spacetime, a kind of localized spacetime explosion. While no classical model supports this, quantum gravity theories allow for unusual spacetime behaviors at extreme energies, such as bubble nucleation, vacuum decay, or dimensional phase shifts. Annihilation might not just destroy matter, it could restructure the very space-time geometry the black holes occupy. There's also the possibility that such a collision could trigger exotic particle production, more than even typical high-energy mergers. The interactions might breach energy thresholds needed to create supersymmetric particles, axions, or dark matter candidates. In this sense, an antimatter-matter black hole collision could act as a natural particle accelerator beyond anything we can build, unlocking a new regime of physics. Of course, all this hinges on the existence of antimatter black holes, which, to be clear, are entirely hypothetical. The observable universe seems to be overwhelmingly composed of matter, and antimatter appears to be rare. One of the biggest open questions in cosmology is why there's such an imbalance between matter and antimatter. Some inflationary models, however, suggest that antimatter could have been segregated into distant regions of the universe during the Big Bang. If so, antimatter black holes might still exist, but they could be billions of light years away, isolated in their own antimatter galaxies or voids. There's also a speculative idea that microscopic primordial black holes, formed during the very early universe, could include both matter and antimatter versions. These black holes, if they still exist, could be as small as an asteroid and might even contribute to the dark matter content of the universe. A collision between a matter and antimatter version of such primordial black holes could produce detectable signals, though they would likely be very short-lived, very intense flashes of radiation, possibly detectable by gamma-ray observatories. In a more dramatic model, some have theorized that annihilation could result in the complete destruction of both black holes, leaving no remnant at all, no final event horizon, no gravitational signature, just energy released outward at relativistic speeds. This would contradict everything general relativity tells us about black hole behavior, but quantum mechanics might offer more flexibility, especially when dealing with antimatter's role in the universe's fundamental symmetries. So, while the idea of antimatter black holes remains speculative, the merger of such an object with a matter-based black hole presents some of the most energetically violent and theoretically disruptive outcomes in theoretical physics. It's a scenario that pushes the boundaries of both general relativity and quantum field theory, demanding a unified theory of quantum gravity to truly describe what would happen. In the meantime, astronomers and physicists continue to search the skies for anomalous gravitational waves or unexplained high-energy events, any of which could hold the fingerprints of such a cosmic-scale annihilation. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.